Look up. The universe isn't drifting through silence. It's twisting. Planets, stars, galaxies, even space-time itself caught in a relentless whirl. From dust grains to black holes, almost everything is born with spin, as if the cosmos can't stand still. So what lit the first match? Who or what gave the universe its initial shove? And why does it never stop turning? In space, rest is almost a myth. Every calm surface hides a stored twist, waiting to be measured. What looks like order from Earth is, up close, a choreography of turning written into matter itself. Spin is not just motion, it is a record, an accounting of how mass once fell, cooled, collided, and refused to settle perfectly. Across the universe, that record survives because the cosmos guards angular momentum with stubborn fidelity, even when everything else changes. Yet conservation can only keep a secret. It cannot invent the first hint of direction. Somewhere between an almost uniform beginning and the first clumps of structure, the universe learned to choose a handedness, then amplified it without mercy. In this film, we follow rotation as it migrates from place to place, traded between orbit and spin, hidden in disks and carried away by jets. We will watch gravity tighten its grip until a slight imbalance becomes a whirling system, then confront the crisis that follows when collapsing gas should spin itself apart. You'll see why some worlds keep their spin for billions of years, while others bleed it away by tides only a few milliseconds per century. You'll meet stars whose surfaces rotate at different speeds, winding magnetic fields into cycles of storm and flare, and you'll trace how newborn systems shed excess angular momentum without losing the material that must become planets. Then the story accelerates toward the extremes, city-sized neutron stars that turn hundreds of times each second, and black holes where rotation becomes geometry. There, spinning is no longer a metaphor but a distortion of space-time, shaping what can orbit, what can escape, and what can never stand still. And through it all, one question remains sharper than any image we can render. If the universe began nearly smooth, why did its structures not form motionless, but instead arrive already turning? The answer is not a single mechanism, but a chain of small imperfections that gravity preserves, magnifies, and redistributes, until spin becomes unavoidable. This is not a tale of cosmic decoration. It is a story about stability, energy, and fate. Rotation decides whether a cloud becomes a star or a disk, whether a galaxy becomes a thin spiral or a scrambled spheroid, and whether collapse ends quietly or detonates with a jet. By the end, we will assemble the universe's rotating inventory, where the angular momentum lives, how it is exchanged, and why it so rarely disappears. In that ledger is a clue to our own origins, because every day on Earth is timed by a relic of the same physics that shapes galaxies. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We'll begin where stillness should exist, then travel back toward a smoother universe to find the first imbalance. From there, we follow gravity's tightening spiral into stars, planets, pulsars, and the rotating edge of relativity, before balancing the cosmic ledger. Rest feels intuitive on Earth, but the cosmos treats stillness as a rare exception. Look up and you're watching motion layered on motion, turning that never fully stops. Even the points of light that seem fixed are drifting, circling, and subtly wobbling across immense timescales. The mystery is not that objects travel through space, but that they keep spinning in place. Start close to home, where the evidence is so familiar we forget it's strange. Earth rotates once every day, and that spin sets the rhythm of light and shadow across continents. The Terminator line slides over oceans like a slow blade, and the atmosphere rides along, dragged by friction against land and sea. At the same time, Earth orbits the Sun, tracing a yearly path that feels separate, like a different kind of motion. One is spin, a body turning around its own axis, and one is orbit, a body circling something else. They look different, but physics links them. Both are forms of angular momentum, the bookkeeping of rotation in the universe, and the rules are surprisingly strict. Angular momentum can be written as L equals I times omega, moment of inertia times spin rate. Moment of inertia is not just mass, it is mass distributed at distance from the axis, which is why shape matters. Change the shape or size of a system and omega can change, but L tends to persist. Earth's rotation is not perfectly steady, and careful clocks can detect its tiny irregularities. The planet flexes under the pull of the moon and sun, oceans surge, and the solid Earth deforms by centimeters. Tides and internal friction slowly bleed spin away, but the process is glacial, measured in milliseconds per century. In the near vacuum between worlds, there is little to grab onto, and almost nothing acts like a brake. Without strong braking forces, rotation becomes the default that lingers. This persistence has a history, and humans learned it long before they had rockets. In the 19th century, Foucault's pendulum made Earth's rotation visible in a quiet room, as the swing's plane seemed to turn beneath the ceiling. Later, precision measurements of Earth's day length tied rotation to oceans, ice ages, and the shifting of mass inside the mantle. Even here, on a world full of friction, spin refuses to vanish quickly. It fades reluctantly because it must be carried away. Move outward, and the inventory of spin becomes stranger and more dramatic to the eye. Jupiter is a giant world that completes a rotation in about 10 hours, and that speed is written into its face. The planet's clouds stretch into bands, winds shear in opposite directions, and storms like the Great Red Spot persist for centuries. Rapid spin also sculpts the planet's shape, making it visibly flattened at the poles and bulged at the equator. Even when the details differ, the pattern repeats. Big objects form, and they almost never form without turning. The reason is partly geometric and partly statistical, and it begins in the chaos of formation. When a cloud of gas and dust collapses, its particles rarely fall straight inward with perfectly cancelling motions. Tiny sideways velocities add up, and as the cloud shrinks, those small swirls become organised rotation. The collapse concentrates mass close to the axis, which lowers the moment of inertia and raises the spin rate. Gravity does not create angular momentum, but it can amplify what is already there. Now shift to the Sun, which looks calm from far away but is not a rigid sphere. Its surface boils with convection cells, and its plasma flows like a restless ocean of ionized gas. The Sun rotates differentially, faster at the equator and slower near the poles, because different latitudes slide past one another without a solid crust. That shear stretches magnetic fields, stores energy, and helps drive cycles of activity that wax and wane over roughly 11 years. Rotation is not a decorative feature, it becomes an engine that shapes what a star does. In visible light, the Sun can seem like a steady disk, but the details betray the churn. Dark sunspots mark concentrated magnetic regions, and their drift across the surface reveals the changing rotation rate with latitude. Loops of plasma arc along magnetic field lines, and sudden flares release stored energy like a snapped rubber band. The solar wind carries particles outward, and the Sun's rotation winds its magnetic field into a spiral shape through the solar system. Even the space around the star remembers the star's turning. At smaller scales, rotation becomes extreme, and the visuals become almost abstract. Neutron stars are the collapsed cores of massive stars, packed into a city-sized sphere with more mass than the Sun. Their matter is crushed to nuclear densities, where a teaspoon would outweigh a mountain, and the surface gravity is fierce. Many spin dozens, hundreds, even more than 700 times per second, and the numbers feel like a mistake. Their beams sweep like cosmic lighthouses, and we detect them as pulsars, regular flashes timed more precisely than many atomic clocks. The logic is simple, even if the outcome is wild. When a star collapses, its radius shrinks dramatically, and its moment of inertia drops by orders of magnitude. If angular momentum is conserved, omega must rise as I falls, and the spin rate surges. It is the same principle as an ice skater pulling in their arms to spin faster, except the skater is a star and the rink is space-time. In some systems, accreting matter can spin a neutron star up further, adding angular momentum like a steady hand on a wheel. This is the first major clue, and it is easy to miss because it sounds like a slogan. The universe is not eager to erase rotation, because the mechanisms that remove it are weak. Space is cold and thin, and friction is scarce on cosmic scales, so there is little to convert ordered spin into heat. Unless something can carry angular momentum away, a system keeps what it has, and sometimes it concentrates it. In that sense, spin is not an exception to the rules. It is what the rules protect. Yet the story is not only about isolated spinning balls, each turning alone in the dark. Across the universe, gravity and rotation repeatedly produce the same geometry, and it appears again and again in telescopes. Matter falls inward, but angular momentum prevents a straight plunge, because sideways motion cannot simply disappear. The result is a disk, a flattened whirlpool where material circles as it sinks. The disk is nature's compromise between falling and missing. Accretion disks appear around young stars, around white dwarfs, around neutron stars, and around black holes. In infrared light, a newborn star can be wrapped in a dusty disk that glows softly, with gaps where planets may be forming. In X-rays, disks around compact objects blaze, because gas is heated to millions of degrees as it spirals inward. They glow because friction inside the disk converts orbital energy into heat and light, and magnetic turbulence helps stir the flow. Even here, the central theme holds. The disk exists because angular momentum must be redistributed, not ignored. The disk is not just a shape, but a process. Inner regions lose angular momentum and drift inward, while outer regions gain it and move outward, like a crowd making room for someone to pass. In some systems, jets erupt from the poles, narrow beams launched along magnetic fields that can carry energy and angular momentum away. The details vary, but the accounting is relentless, and the system must balance its books. Gravity pulls in, angular momentum pushes out, and the disk mediates the argument. Zoom farther out and the whirlpool motif becomes a galactic signature, drawn across tens of thousands of light years. Many galaxies are spirals, with arms that trace rotating disks of stars and gas, and their silhouettes look like cosmic fingerprints. Dust lanes cut dark curves through starlight, while pink nebulae mark regions where new stars ignite. The Milky Way is one of them, and the Sun rides inside that rotation, embedded in a disk that turns around a central bulge. Galaxies do not merely drift through space, they carry coherent spin that can persist for billions of years. Spiral structure is not a simple pinwheel of fixed material arms, and that subtlety matters. The arms are patterns shaped by gravity, density waves, and ongoing star formation, so stars move in and out of them like cars passing through a traffic jam. Gas clouds compress as they enter the denser regions, and that compression triggers bursts of starbirth that light up the arms. Still, the presence of a rotating disk is fundamental, because the disk is the reservoir of angular momentum. Without angular momentum, a galaxy would collapse into a more compact, less ordered shape. Then there are the darkest rotators of all, where the language of everyday motion starts to fail. A rotating black hole is described by the Kerr solution, where spin changes the structure of spacetime itself. Near such an object, frame dragging twists the paths that matter and light can take, as if the geometry is being stirred. Spacetime is pulled into a slow whirl, and nothing nearby can remain completely still, not even the vacuum. The region called the ergosphere becomes a place where rotation is unavoidable, because the very notion of standing still breaks down. This is rotation pushed into relativity, where the question becomes more than mechanical. Spin is not only a property of matter moving in space, like a wheel turning on an axle. In extreme gravity, spin reshapes what space and time allow, altering orbits and shifting the boundaries of what can escape. The universe contains objects whose rotation is written into the geometry around them, and that geometry can, in turn, influence how matter falls and radiates. It is a reminder that angular momentum is not a small detail, but a fundamental organizing principle. So the inventory is overwhelming, and it spans scales that barely fit in the same imagination. Planets spin and orbit, and their climates and tides remember that motion. Stars rotate, sometimes differentially, and their magnetism remembers that motion as well. Dead stars spin faster than intuition allows, because collapse amplifies what was already there. Galaxies turn, disks form, spirals appear, and black holes drag the stage itself. At this point, it helps to sharpen definitions, because language can blur what physics keeps separate. Orbiting is angular momentum in a path around a center, and spinning is angular momentum around an internal axis. Both can be described with the same conserved quantity, even though one looks like a loop and the other looks like a twist. The same quantity can be exchanged between them through tides, collisions, and gravitational interactions, and those exchanges leave fingerprints. A moon can steal spin from a planet and move outward, and a collapsing cloud can trade random motion for organized rotation. Angular momentum is conserved when no external torque acts, and that statement is as central as energy conservation. It feels less familiar because daily life is soaked in friction, and friction supplies torques everywhere. A spinning top slows because air drags on it, and the surface pushes back, stealing angular momentum bit by bit. In space, the environment is different, and conservation becomes visible, like a rule written in bright ink. The emptiness between worlds does not erase motion, it preserves it. A rotating system can slow down, but it must send angular momentum somewhere, and that somewhere is often visible if you know what to look for. It can radiate it away through winds and jets, or transfer it to a companion, or redistribute it internally. Accretion disks can fling material outward while feeding a center inward, and those outflows can shape nebulae and carve cavities. Stars can shed spin through magnetic braking, but only if they have a medium to couple to, like a wind that can be torqued by magnetic fields. Without a channel for export, rotation remains trapped in the system. This is why the universe looks like a museum of persistent rotation, filled with exhibits that keep turning long after their formation. Once a cloud, a planet, or a star acquires a twist, it tends to keep it, because there is no easy way to pay it off. Gravity can compress and amplify that twist, turning gentle rotation into rapid spin, and the effect can be dramatic. Mergers can add spins together, or tilt axes, or create new disks from chaos, leaving systems misaligned like a scar. Even apparent disorder often hides a conserved quantity moving from one place to another. Still, conservation is not a full origin story. It explains why spin survives and why it can grow when things shrink, but it does not explain why the first rotation existed at all. Conservation preserves what is present, but it cannot create angular momentum from nothing, any more than it can create energy from nothing. If we rewind the cosmic film far enough, we eventually confront the first frame where the turning begins. The question becomes less about endurance and more about origin. That gap is where the deeper mystery lives, and it is sharpened by what we think we know about the beginning. The early universe after the Big Bang is often described as hot, dense, and nearly uniform, a plasma so energetic that atoms could not yet form. On the larger scales, it had only tiny fluctuations, a smoothness measured in the cosmic microwave background. That ancient light is a snapshot of a young cosmos, and its temperature variations are only parts in 100,000. If the beginning was almost featureless, why is the later universe so full of organized turning? One answer points to primordial fluctuations, the small irregularities that seeded structure. If density was not perfectly uniform, gravity could amplify those differences, drawing matter into slightly denser regions. As regions collapsed into halos and galaxies, small asymmetries could become large rotations because perfect symmetry is fragile. Even a slight imbalance can be magnified when matter falls inward, and the collapse acts like a lens for motion. What begins as a barely measurable unevenness can end as a spinning disk of stars. Another answer emphasizes tidal torques, a mechanism that is almost inevitable in a clumpy universe. Proto-galaxies do not form in isolation, and nearby clumps tug on each other as they grow, stretching and twisting the distribution of matter. Those gravitational pulls can torque collapsing regions, injecting angular momentum before they fully condense into stable structures. Spin can emerge as a collective outcome of many interactions, not as a single initial spin, and the direction can depend on the local environment. In that view, rotation is a social phenomenon, produced by neighbours. Mergers add another layer, and they are common in a universe built hierarchically. Galaxies collide, and their orbital angular momentum can be converted into internal rotation, like a dance turning into a spin. Disks can be disrupted and rebuilt, and the remnant can carry a new axis that remembers the encounter. Black holes can gain spin by swallowing matter with a preferred direction, and by merging with other black holes whose orbits carried angular momentum. In a universe that grows by assembly, spin can be continually manufactured from orbital motion. Relativity also enters the conversation, because gravity is not just a force in space, and the geometry matters. In general relativity, mass and energy shape space-time, and motion follows that curvature, which changes how systems exchange energy and angular momentum. Rotating mass distributions can produce subtle effects that influence how angular momentum is transported and how systems settle into equilibrium. The extreme case is frame dragging, but the broader point is that rotation and gravity are deeply coupled. When the stage bends, the dance changes. These ideas compete and overlap, and each has limits that keep the mystery alive. Tidal talks can explain typical galaxy spins, but not every detail of alignment and magnitude across different environments. Mergers can spin up some systems while randomizing others, and they can also destroy delicate disks that took eons to form. Primordial conditions set the stage, but they must connect to the messy history of structure formation, where feedback, turbulence, and chance encounters matter. The universe offers clues, but it rarely offers a single clean cause. The tension remains productive because it points to a single question beneath the inventory. If almost everything we see is rotating, then rotation is not an accident of a few special cases or a quirk of our neighbourhood. It is a common outcome of the universe's rules, plus whatever initial irregularities those rules acted on, and those irregularities were small. Why should small asymmetries so reliably become large, coherent spins, rather than cancelling into stillness? What does it mean that the cosmos seems to prefer turning over resting? So Chapter 1 ends with two linked claims, and they frame what comes next. First, the cosmos is not built around rest because angular momentum is hard to erase in near vacuum, and the evidence is everywhere you look. Second, conservation explains persistence and amplification, but it does not explain the first twist, the initial departure from perfect symmetry. To answer why everything spins, we have to go back to where motion begins, in the earliest moments after the Big Bang. Still, conservation is not a full origin story, because it tells us why spin survives, but not how the first twist appeared. Conservation can protect a quantity once it exists, yet it cannot explain the moment the universe first chose a direction. That missing moment is the gap in the narrative, the place where symmetry breaks and a preference is born. In physics, symmetry is not only aesthetic, it is a rulebook that says many outcomes should be equally likely. When one outcome wins, even slightly, a story begins. To find that first imbalance, we rewind to the early universe, to conditions so extreme that ordinary intuition fails. The Big Bang is not an explosion into empty space, with debris flying outward from a central point. It is an expansion of space itself, with distances growing everywhere at once, even between regions that are not moving through space. In the visuals, imagine a grid painted on the fabric of space-time, and then watch the grid stretch uniformly, as if the ruler itself is being pulled longer. Galaxies are not shrapnel racing through a void. They are passengers carried apart by the widening of the road. Expansion can look like motion, but it is not rotation, and that distinction matters. In cosmology, expansion is described by a changing scale factor, AET, which multiplies the distances between co-moving points. Rotation would mean something else entirely, a preferred axis in the large-scale flow of matter, a built-in handedness to the universe's geometry. If expansion is a swelling balloon, rotation is a slow spin of the balloon, an added pattern that would show up in how matter streams. One changes the size of the map, the other changes the direction of the compass. The central question sharpens here, because the universe seems to produce spin at every scale we can resolve. Galaxies rotate, stars rotate, planets rotate, and even many asteroids tumble with stubborn persistence. Why does the universe produce spin so reliably if the beginning was almost smooth and almost directionless? What started rotation in the first place if there was no obvious cosmic wheel to set it going? And if the early cosmos had no preferred direction, why do so many later systems behave as if turning is the default? Early on, the universe was hot plasma and radiation, nearly uniform in density, and intensely bright in every direction. Protons and electrons had not yet combined into neutral atoms, so photons scattered constantly, like light trapped in a dense fog. That near uniformity is not a guess, and it is not a philosophical preference for simplicity. It is measured in the cosmic microwave background, the afterglow of the young universe, released when the fog finally cleared. That clearing, recombination, happened hundreds of thousands of years after the beginning, when the temperature fell enough for atoms to hold together. The CMB is remarkably isotropic, with tiny temperature variations across the sky that look like faint freckles on an otherwise smooth sphere. Those variations are about 1 part in 100,000, a precision that still feels almost implausible. They are the seeds of everything that later clumps. because gravity needs only the slightest head start. In a full sky map, the largest features span tens of degrees, while the smaller ones form a delicate grain, an ancient pattern frozen in light. The pattern is not random noise, it is structured randomness, shaped by physics that operated before any star existed. If the universe had a strong global rotation, the CMB would likely show it, and it would show it in more than one way. A rotating cosmos tends to imprint large-scale anisotropy, including distinctive patterns in temperature and polarization, because rotation introduces shear and preferred directions. The imprint would not be subtle, like a hidden watermark, but more like a systematic distortion across the whole sky. We do not see such a dramatic signature, and that absence is itself a powerful clue. It suggests that if there is a cosmic spin, it is buried far below the level of the CMB's already tiny irregularities, so the suspense lands on a careful distinction that cosmologists return to again and again. The universe can have near zero net rotation overall, while local regions still acquire spin through later interactions. Global vorticity can be constrained, while local angular momentum can be common because cancellation is allowed. A river can have no net swirl downstream, while still hosting countless eddies that twist and vanish along the banks. The average can be calm, even when the details are restless. Inflation enters as the leading explanation for this smoothness, and it arrives with a kind of narrative audacity. It proposes a brief era of accelerated expansion in the earliest fraction of a second, when the scale factor grew almost exponentially. Inflation stretches space so rapidly that curvature and pre-existing irregularities are diluted, like wrinkles ironed out by a sudden, violent pull. In the visual language of the film, the early universe becomes a surface being stretched so fast that bumps flatten before they can matter. Historically, inflation was proposed to address puzzles like the horizon and flatness problems, and its success is tied to how well it explains the CMB's uniformity. Inflation also provides a mechanism for imperfections, and the mechanism is not mechanical in the everyday sense. Quantum fields cannot be perfectly quiet, even in their lowest energy state, because uncertainty is built into their description. They fluctuate inherently, without needing a push or an external disturbance, and those fluctuations are not errors. They are the unavoidable jitter of reality at microscopic scales, a restless baseline that no cooling can fully remove. Even empty space in quantum theory is not empty in the ordinary meaning of the word. During inflation, microscopic quantum fluctuations are stretched to astronomical scales, and that stretching converts quantum randomness into classical-looking structure. What begins as a tiny variation in a field becomes a macroscopic pattern in density, because the rapid expansion freezes the fluctuation into the fabric of spacetime. That pattern later becomes the blueprint for galaxies and clusters, long before any star ignites. In animation, the noise of quantum ripples becomes a faint mottling across a growing cosmic canvas. The remarkable twist is that a fluctuation that began smaller than an atom can end up spanning light years. These fluctuations are random, but their statistics can be predicted, which is one of inflation's most striking features. They are close to scale invariant, meaning similar power across many sizes, with a slight tilt that encodes the physics of the inflationary era. Observations of the CMB broadly match that expectation, and the match is not just qualitative. The peaks and troughs in the CMB power spectrum line up with a model in which sound waves once rang through the primordial plasma. Those peaks are like a fossilized chord, pressure pushing outward, gravity pulling inward, and the universe recording the rhythm. At this stage, the universe is expanding and cooling, and matter is still mostly smooth, yet the seeds exist as slight overdensities and underdensities. Gravity is weak per particle, but it is relentless in aggregate because every bit of mass contributes. A tiny excess in density means a slightly deeper gravitational potential, and that potential quietly reshapes motion over millions of years. The film can linger here on the idea of patience, gravity as a slow accountant, adding small advantages until they become decisive. What looks like stillness is actually a long negotiation between expansion and attraction. When a region is slightly denser than average, it slows its expansion relative to its surroundings, because gravity pulls inward against the Hubble flow. Over time, that region becomes a gravitational well, and the well becomes more defined as matter drifts inward. The contrast grows, first gently, and then more quickly, as the overdensity begins to decouple from the general expansion. In a visual, the overdense patch is a subtle depression in a field, deepening until it becomes an unmistakable basin. The basin does not appear all at once. It sharpens as more matter commits to the inward fall. This is the growth of structure from tiny bumps, and in the early regime the mathematics is surprisingly clean. In linear theory, the equations are simple enough to solve with clarity, because perturbations remain small and do not strongly interact. Density perturbations grow, velocities develop, and the flow is mostly irrotational, meaning it is dominated by gradients rather than curls. The universe, at first, behaves like a fluid sliding downhill in a potential landscape, not like a storm full of vortices. That early simplicity is deceptive, because it contains the seeds of later chaos. Irrotational means the velocity field has little curl, and curl is the mathematical signature of local spinning motion. In the early linear regime, vorticity decays with expansion in standard cosmology, because the stretching of space damps rotational components faster than compressive ones. That seems to argue against primordial swirling in the matter flow, at least in the simplest picture. If the universe began with tiny curls, the expansion would tend to smooth them away, leaving a flow that is mostly straight and convergent. In other words, the early cosmos forgets rotation more easily than it forgets density. Yet the universe we observe is not linear forever, and it does not remain a single, well-behaved stream. Collapse becomes non-linear when overdensities grow large, and then the tidy approximation breaks. Shells of matter cross, shocks form in gas, and simple potential flow breaks down, because different trajectories intersect in the same region of space. The moment of shell crossing is a kind of narrative threshold. After it, complexity is no longer optional. In simulations, this is where smooth gradients fracture into knots, and the cosmic web begins to look like a living network. This is where vorticity can appear, even if it started tiny, because nonlinear dynamics can generate curl from initially curl-free conditions. Nonlinear structure formation generates complexity in velocity fields, and complexity is fertile ground for rotation. The curl can be sourced by multi-streaming pressure gradients and turbulent cascades, each adding its own layer of twisting motion. In a simulation, the once smooth velocity arrows begin to tangle, and the flow develops eddies that were not present in the linear era. The universe does not need to start with a swirl if it can manufacture swirls through evolution. The key move is local differentiation, and it is the universe's way of creating variety without breaking its overall statistical symmetry. Even if the global universe is statistically uniform, local patches evolve differently, because their environments differ in subtle but consequential ways. Small differences in geometry, neighbouring mass, and timing change how collapse proceeds, and those differences amplify. The film can show identical seeds placed in different neighbourhoods, then watch them diverge into distinct fates. A tiny offset in alignment can decide whether a halo becomes a quiet spinner or a violently reoriented system. Imagine a patch that will become a galaxy halo, a future home for stars and gas, long before it looks like anything familiar. It is not a perfect sphere, and its surroundings are not symmetric because the primordial density field is a random superposition of modes. Nearby overdensities pull unevenly, and those tidal forces matter, because gravity is sensitive to shape. The protohalo is more like an irregular lump of clay than a smooth ball, and the universe around it is a shifting scaffold. In close-up visuals, you can almost see the lump being stretched along one axis, while being squeezed along another. Tidal torques provide a natural route to spin, and the idea has a long history in cosmology's attempt to explain rotation without invoking a spinning universe. As a protohalo collapses, external gravitational fields stretch it, and stretching is not just deformation. The misalignment between its mass distribution and the tidal field produces a torque, a twisting influence that changes angular momentum over time. In visuals, torque arrows appear where the halo's elongated axis fails to line up with the direction of the external pull. The torque is not a mysterious force. It is gravity acting with leverage, because the mass is distributed off-center. This torque does not require a primordial rotation of the whole universe, and that is why it is so attractive as an explanation. It converts the orbital and shear motions of neighbouring matter into angular momentum of the collapsing region, as if the environment spins up the halo through gravitational leverage. It is a local accounting, not a cosmic preference, and it works even if the universe has no overall axis. The twist is borrowed from the surrounding mass distribution, not inherited from a universal spin. One region gains angular momentum, another loses it, and the total can still sum to nearly zero. In the early stages, the torque builds gradually, because the proto-halo is still expanding with the universe and has not yet collapsed. Angular momentum grows as the proto-halo expands with the Hubble flow, then slows and turns around when gravity wins locally. By the time it collapses and virializes, reaching a quasi-equilibrium between kinetic and potential energy, it carries a measurable spin. That spin is not a dramatic whirl at first, but it is enough to matter later, because conservation will preserve it through further evolution. The moment of turnaround is especially important. After it, the system's internal motions begin to dominate over the universal expansion. The mechanism is statistical, but it is widespread because structure forms in a web of filaments and nodes rather than in isolation. Every collapsing region has neighbours, and neighbours exert tides, and tides rarely align perfectly with a region's internal shape. In the cosmic web, matter streams along filaments like traffic on invisible highways, and intersections become nodes where halos grow. The very connectedness of the web ensures that tidal influences are almost unavoidable. In wide shots, filaments glow faintly in simulated density, converging into bright knots like dew, collecting at the low points of a spider's web. This begins to answer the tension from Chapter 1, where we learned how stubborn angular momentum can be once it appears. If spin is hard to erase, then even modest torques concede lasting rotation, and the universe does not need a huge initial twist. The question becomes whether these torques are strong and universal enough across masses and environments. Is the cosmic web a reliable factory for spin, or does it merely supply occasional accidents that later get amplified? And if it is reliable, what sets the typical amount of spin, and why does that typicality persist across cosmic time? But we should not skip the global question too quickly, because it is part of the mystery's deeper appeal. Could the universe itself have had a primordial rotation? A built-in vorticity of spacetime, however faint? If so, it would add a baseline twist to everything, like a slow turning of the stage beneath the actors. Even a tiny global rotation might bias the direction of spins, leaving a subtle fingerprint in the distribution of angular momenta. The appeal is almost philosophical. If the universe had a preferred direction, what would that say about the symmetry of the laws we trust? General relativity allows rotating cosmological solutions in principle, and the history of cosmology includes serious exploration of such possibilities. Some models include global vorticity, shear or anisotropic expansion, and they are mathematically consistent within Einstein's equations. In these solutions, spacetime itself carries a kind of rotational character, and inertial frames can be dragged in a coherent way. Nature, however, must choose them, and the universe we observe must bear their consequences. The lesson of 20th century cosmology is that elegant solutions are plentiful, but the sky is the final arbiter. Observations act as the judge, and they do so with a severity that theory cannot evade. The CMB provides the cleanest test because it is a full sky relic from early times, a snapshot from an era when matter and radiation were tightly coupled. Large-scale rotation would imprint preferred directions and correlated patterns, not only in temperature but also in polarization. The CMB is like a forensic surface. If the universe spun, it should have left marks. The remarkable thing is that we can read those marks across the entire sky, as if the cosmos kept its own record. Searchers look for anomalies beyond the standard random fluctuations, and they do it with increasingly refined statistical tools. They test for dipoles, quadrupoles, and higher multipoles with unusual alignments, because rotation can couple modes in characteristic ways. They also test polarization patterns that could betray cosmic shear, including subtle correlations between E modes and B modes. The analysis is delicate because foreground emission and instrument systematics can mimic patterns that look cosmological. In the film's visuals, layers of contamination peel away, dust, synchrotron glow, until the faint primordial signal remains. So far, constraints are tight, and they have tightened with each generation of CMB experiments. Any global rotation rate must be extremely small compared to the expansion rate, often expressed as a tiny fraction of the Hubble parameter. If the universe spins at all, it spins so slowly that it does not dominate structure formation, and it cannot be the main source of the spins we see in galaxies. The cosmos, at least on the larger scales, behaves as though it has no preferred rotational axis. That conclusion is not a disappointment. It is a clue that points us toward local, repeatable engines. That conclusion is not merely negative, because it forces the story to become more interesting rather than less. If there is no strong primordial spin, then spin must be generated during structure formation, and it must be generated repeatedly. The universe must be able to manufacture angular momentum from the geometry of collapse and the interactions between neighbours. The mystery shifts from what was the initial spin to what is the engine that keeps producing spin. The answer cannot be a one-time event. It must be a process that operates wherever matter gathers. Yet another subtlety remains, and it is easy to miss if we think only in terms of totals. Even with zero net rotation, the universe can contain equal and opposite angular momentum in different regions, because angular momentum is a vector. Local spins can cancel globally, like eddies in a river that sum to no overall swirl when averaged across a wide channel. In that picture, the universe can be globally unbiased while still being locally full of twists. The absence of a cosmic axis does not imply the absence of turning. It implies only that turning has no universal sign. This is consistent with the CMB's near-isotropy, because isotropy constrains coherent, large-scale patterns rather than small-scale cancellations. The early universe can be smooth on large scales, while still containing the seeds for local asymmetry, because the seeds are statistical rather than directional. The seeds are not spins yet, but they enable torques later by creating lumpy environments. The universe does not need to begin with rotation, only with the possibility of misalignment. The question becomes almost surgical. Where does misalignment first become a torque, and where does torque first become a lasting spin? The growth from density bumps to rotating systems is not instantaneous, and the timeline matters for understanding what causes what. First, dark matter collapses into halos because it does not feel radiation pressure and it interacts primarily through gravity. Baryonic gas falls into those halos later, cooling and dissipating energy through radiation, and that dissipation changes the outcome. The dark matter sets the gravitational stage, while the gas performs the luminous drama we can actually see. In visuals, the dark matter is a translucent scaffold, while the gas is the glowing paint that reveals the structure. Dissipation changes the geometry in a way that is visually striking and physically decisive. Gas can radiate heat and settle into a disk, while dark matter remains in a puffier halo with a more isotropic velocity distribution. The disk's rotation reflects the angular momentum acquired by the combined system, but it also reflects how the gas rearranges that momentum as it cools. In a montage, diffuse gas streams inward, shocks, glows, and then flattens into a thin, rotating plane. The flattening is not cosmetic. It is the gas finding the only shape that can keep falling, while still respecting its angular momentum. This is where the familiar spiral galaxy becomes possible, and the disk becomes a kind of organizer of motion. A rotating disk is a compromise between gravity pulling inward and angular momentum resisting direct collapse, because angular momentum acts like a barrier to falling straight to the center. The disk is not the origin of spin, but it is the structure that makes spin visible and persistent. Spiral arms then appear as patterns in the disk, shaped by density waves and instabilities, tracing rotation like ink in moving water. In close-up shots, star-forming regions light up along the arms, like sparks riding a turning wheel. In linear theory, the early velocity field is mostly a gradient flow, and that is why vorticity is expected to be small at first. A gradient flow means it can be derived from a potential, with velocities pointing down the steepest descent of the gravitational potential. Such flows converge and diverge, but they do not swirl, at least not in the strict mathematical sense. The early universe, in this approximation, is a place where matter falls inward without yet learning to turn. The simplicity is powerful, because it tells us that rotation is not primordial by default, it is earned. But the universe does not stay linear, and it does not stay single stream, because gravity inevitably creates crossings. As matter collapses, trajectories cross and caustics form, producing sharp features in phase space where densities spike. The velocity field becomes multi-valued, because different streams occupy the same location with different velocities, and effective vorticity emerges. In a visualization, phase space sheets fold over themselves, and the simple arrow field becomes layered and ambiguous. The cosmos begins to resemble a braided flow, multiple histories passing through the same point. For gas, additional sources appear, and they are rooted in fluid dynamics rather than purely gravitational kinematics. Shocks can generate vorticity when pressure and density gradients misalign. a baroclinic effect that converts compressive motion into rotational motion. Baroclinic twisting is especially important in complex accretion along filaments, where gas arrives with different temperatures and densities. The cosmic web is not only a gravitational scaffold, but also a network of colliding flows that can stir the gas. In visuals, you can show shock fronts as bright arcs, and behind them the gas begins to curl, as if the collision taught it to spin. So vorticity in cosmology is partly a story of timing, and partly a story of which component we are talking about. Early on, expansion damps primordial curl and favours potential flow, especially for collisionless dark matter. Later, nonlinear collapse and hydrodynamics generate curl in abundance, particularly in baryonic gas where shocks and cooling complicate motion. The universe begins as a nearly laminar flow, then gradually becomes a turbulent, structured medium where rotation is common. The transition is not a single moment, it is a gradual tipping of the balance from smooth descent to tangled circulation. This timing matters for the documentary's mystery, because it tells us when the first reliable spins could have been produced. If the early universe did not spin as a whole, then the later universe must manufacture spin reliably, and it must do so before galaxies fully assemble. The mechanism must operate across environments, masses, and cosmic time, from small halos to giant clusters. It must also be robust against randomness, because the universe does not get to retry a galaxy that fails to spin. The reliability is the clue. Whatever the engine is, it must be generic to gravity acting on lumpy matter. Tidal torque theory is the leading candidate for the first spin-up of halos, and it has been refined through decades of analytic work and numerical simulation. It predicts a distribution of dimensionless spin parameters, not a single value, because different environments produce different torques and collapse histories. Simulations show that typical halos acquire modest spins consistent with this picture, and the distribution is broad but stable. The theory does not claim that every halo spins the same way, only that the cosmic web makes spin statistically inevitable. In the film, graphs can fade into rotating halos, linking abstract parameters to visible motion. But the details are messy, and that is where suspense lives, because messy details are where simple stories break. Halo spins can change through mergers, accretion, and interactions, and those changes can be abrupt. Disks can flip, warps can form, and angular momentum can be redistributed between components, including transfers between baryons and dark matter. In a sequence of visuals, a calm rotating disk is disturbed by an incoming satellite, and the disk bends, thickens, or reorients. The question is not whether spin exists, but how it survives violence, and how often it must be rebuilt. Even so, the broad narrative is consistent, and it remains one of modern cosmology's most satisfying chains of cause and effect. Small initial density variations create a lumpy universe, and that lumpiness creates tidal fields that vary from place to place. Tidal fields torque collapsing regions and seed angular momentum, which is then conserved and reorganized as structures form. From the faint freckles of the CMB to the bright pinwheels of spiral galaxies, the path is long but traceable. The universe turns imperfection into motion, and then uses conservation to keep the motion alive. This is a chain from near uniformity to widespread rotation, and it does not require a primordial cosmic spin, only primordial imperfections. It matches the conclusion theme that spin is the universe's memory of imperfection, because angular momentum preserves the record of earlier symmetries. A galaxy's rotation is not just a present-day motion, but a fossil of ancient misalignments and gravitational negotiations. When we measure a rotation curve, we are reading a history written in velocity. The curve is a signature, but it is also a narrative: how matter fell in, how it was torqued, and how it settled. Still, we should keep the global question open for one more beat, because science advances by testing even the ideas that seem disfavoured. Some observed anomalies in the CMB have tempted speculation about preferred directions, including unusual alignments at large angular scales. Most are consistent with statistics, foregrounds, or systematics, but the debate keeps the mystery alive. The universe, it seems, is smooth enough to hide a secret, yet structured enough to invite suspicion. If a faint global twist exists, it would be a whisper beneath the louder story of a local talks. The cautious position is clear, and it is anchored in the weight of evidence rather than in aesthetic preference. The universe is consistent with being globally non-rotating to high precision, and isotropy holds remarkably well when tested across the sky. any primordial rotation is constrained to be tiny, and it cannot be the main driver of everyday cosmic spin. If there is a cosmic twist, it is too faint to explain the vivid rotations we observe in galaxies and smaller systems. That forces us to respect the ordinary engine, gravity working on a symmetry, because it appears sufficient. So the story pivots from cosmology to mechanics, and the pivot is not a change of subject so much as a change of scale. If rotation is not handed down as a universal initial condition, then it must be generated locally and repeatedly as structures assemble. That means we need a robust engine that turns collapse into spin, and we need to understand its operating principles. We're no longer asking only what the universe was like, but how it builds what comes next. The camera moves from the whole sky to the neighbourhood, from global smoothness to local leverage. The engine is not a literal motor, and it does not require exotic forces beyond gravity and known physics. It is the gravitational interaction between uneven mass distributions, plus the conservation laws that preserve the result once generated. Gravity amplifies density contrasts, and torques convert a symmetry into angular momentum, producing rotation as a byproduct of uneven collapse. The universe does not spin because it must, but because it cannot collapse in a perfectly symmetric way. Perfect symmetry would forbid a twist, yet perfect symmetry is precisely what quantum fluctuations and tidal environments refuse to provide. This sets up the next chapter's focus, where we move from seeds to machinery with a tighter lens. We move from early perturbations to the processes that spin up halos, disks, stars, and black holes, following angular momentum as it is generated, transported, and locked in. We will watch it flow along filaments, shift during mergers, and settle into rotating structures that endure. The goal is not just to name the mechanism, but to see it at work. In visuals, the abstract arrows of torque become the concrete rotation of disks and the measured spins of halos. They look different, but physics links them, and that link is the chapter's final connective tissue. Expansion sets the stage, fluctuations write the script, and gravity supplies the turning, converting slight irregularities into lasting motion. The universe begins almost smooth, yet it ends up full of rotating systems, each carrying a trace of the first imbalance. The question is not whether imperfection existed, but how imperfection became a twist. And once we see that transformation, we can start asking a sharper question. What determines the direction, the magnitude, and the survival of the spin? Chapter 2 ends with a sharpened mystery rather than a closed case, because the evidence points in a direction without exhausting the story. The early universe was smooth enough to hide any global spin, and inflation helps explain why that smoothness is so extreme. Yet it was imperfect enough to guarantee local twists, once gravity had time to work and once collapse became nonlinear. The cosmos did not begin as a whirlpool, but it learned to swirl. The turning we see is not a leftover from creation, it is a consequence of creation's slight unevenness. Now we ask the practical question that follows, and it carries us forward with purpose. What mechanism produces spins so consistently during structure formation, and how does it shape everything that forms afterward? If angular momentum is the universe's memory of imperfection, then the next step is to watch memory being written. One torque, one collapse, one rotating system at a time. Look up at the night sky and you're watching a universe that refuses to keep still. Even on a calm, moonless night, the scene is restless. Stars drift with Earth's rotation, galaxies wheel in long exposure, and the Milky Way arches like a river that never freezes. The real mystery isn't that things move, because motion is everywhere in physics. The mystery is that almost everything spins, and it spins with a persistence that seems to outlast chaos. Chapter 2 traced the first imbalance, from a smooth beginning to lumpy structure. Now the story tightens around the engine that turns lumps into rotation. Gravity does not invent angular momentum from nothing, and it does not need a cosmic hand to start the wheel. Instead, gravity amplifies tiny borrowed twists until they dominate what forms, and it does so with cold consistency. The central rule is conservation of angular momentum, and it is brutally simple. Angular momentum, L, equals moment of inertia, I, times spin rate, O, and the relationship is more than a formula. It is a constraint on what collapse is allowed to do, because nature keeps strict accounts. If external torques are small, L stays nearly fixed through collapse, even while everything else changes. Moment of inertia is the part that makes the rule feel physical rather than abstract. It depends on how mass is distributed relative to an axis, and for many shapes it scales roughly like mass times radius squared. When a cloud contracts, I drops because mass moves closer to the axis, and that geometric change is decisive. If I goes down, O must rise because L cannot simply disappear into the dark. This is the figure skater logic, but the cosmos performs it at absurd scale. A skater pulls in her arms, reducing I, and the spin rate climbs until the motion looks almost unreal. Now replace the skater with a cloud light years across, and replace the rink with a forming galaxy. The same bookkeeping applies, but the numbers stretch across millions of years and trillions of tons. A diffuse region can begin with only a slight sideways drift, barely distinguishable from the overall flow. That drift can be so small it looks like noise in the early motion, a minor mismatch in velocities. Collapse turns that noise into a measurable spin, because shrinking multiplies rotation in a way that feels like a trick. The same mass, packed tighter, must spin faster to keep the same L, and the increase can be dramatic. If you could watch collapse in accelerated time, the visuals would be unmistakable. A faint misty patch would thicken, its edges drawing inward, while subtle streaming becomes a coherent swirl. The swirl would sharpen as the radius shrinks, like a slow whirlpool tightening into a vortex. Nothing supernatural happens, only the geometry of contraction forcing motion into rotation. But conservation alone still feels like a sleight of hand without a source. If L is conserved, where does the first L in a forming galaxy come from, and why is it rarely zero? The answer is that perfect symmetry is rare, and the universe is never perfectly alone. Proto-galaxies grow inside a crowded gravitational landscape, where neighbours tug with leverage and time. This idea has a history, because scientists have long struggled with cosmic rotation. Early thinkers imagined primordial whirlpools, or a universe born with a grand spin, because rotation seemed too organised to be accidental. As cosmology matured, the emphasis shifted toward growth from small perturbations, and the question became more precise. If the early flow is nearly irrotational, what mechanism reliably generates the spin we observe? Tidal torque theory puts that mechanism at the centre of the story. Start with an extended patch of matter that will later become a halo, and picture it as a lumpy, stretched region. It is not a perfect sphere, and its density is not perfectly centred, even in the simplest models. Surrounding structures create a tidal field that pulls harder on some parts than others, like gravity with long fingers. Uneven pulls on an extended object create a torque, even if the net force points inward. Torque is the rotational cousin of force, and it depends on leverage, not just strength. In equations, it is the cross product of a position vector and a force, which is a compact way to say off-center matters. In plain language, gravity can twist you even while it drags you down. An accessible analogy is a door pushed at different distances from its hinges. The same push, applied near the hinge, barely rotates the door, even though the force may be strong. Apply that push near the handle, and the door swings easily because the lever arm is longer. A proto-halo is like that door, except the hinges are its centre of mass, and the pushes come from all directions. Neighbouring over-densities supply the off-centre pulls, and the geometry does the rest. The result is a slow spin-up while the region is still expanding and stretching, long before it becomes a galaxy. This is important, because it means rotation is acquired early, during the quiet phase of growth. By the time collapse becomes violent, the region already carries a rotational memory. In the early phase, the proto-halo is not yet a bound object, and it does not behave like a finished system. It expands with the Hubble flow, the general swelling of space that carries matter outward on average. Then it gradually slows relative to the background, because its own gravity resists the expansion. As it approaches turnaround, when expansion halts and infall begins, the tidal field has had time to torque it. Angular momentum grows roughly as the region's size and quadrupole moment evolve, and those words hide a vivid picture. A quadrupole moment is a measure of how stretched and uneven the mass distribution is, compared with a sphere. If the patch is elongated and the tidal field is misaligned with that elongation, the torque is efficient. If the patch were perfectly symmetric, the torque would largely cancel, but symmetry is a fragile ideal. By the time it collapses and virializes, it carries a non-zero L that will be hard to erase. Virialization is the moment a chaotic infell becomes a bound structure, with kinetic and potential energies settling into balance. The halo is not calm, but it is stable enough to act as a container for later evolution. From then on, angular momentum is not a temporary detail, it is part of the system's identity. This matters because the early universe does not need to start with swirling motion. The flow can be mostly irrotational in linear theory, as Chapter 2 emphasized, meaning it can be described as gradients rather than curls. Rotation appears because the mass distribution is lumpy and misaligned, and because gravity links lumps across distance. The torque is not internal magic, and it is not a violation of conservation. It is gravity acting through geometry. There is a subtlety here that makes the story feel more realistic. The torque does not act forever with the same strength, because the environment changes as structures grow. Neighbouring lumps move, merge, and reshape the tidal field, sometimes increasing spin and sometimes reducing it. Even the direction of the torque can drift, which means the spin axis is never guaranteed to be permanent. The cosmic web provides the setting that makes these torques unavoidable. Matter does not collapse as isolated spheres sprinkled through empty space, and it never did. It streams along filaments and drains into nodes, building halos by continuous infall that resembles a slow, gravitational weather system. Filaments are not perfectly straight, and inflows are not perfectly balanced, so every channel of supply carries a directional bias. Imagine the web in a simulation view, where density becomes luminous like fog under a flashlight. Thin strands stretch for tens of millions of light years, and knots brighten where many strands intersect. Along those strands, matter flows like traffic on invisible highways, accelerating as it approaches the deep potential wells. In that motion, angular momentum is not rare. It is the natural byproduct of uneven arrival. In this web, direction is local, not universal, and that is a key to the later mystery of misalignment. One filament can feed a halo from one side earlier than the other, creating a sustained torque over long periods. Another filament can deliver a satellite with its own orbital angular momentum, which is often larger than the halo's internal spin. The net spin becomes the vector sum of many contributions, some reinforcing and some cancelling, like competing currents. The outcome is a distribution of spins, not a single cosmic preference. Even if the physics is universal, the initial conditions and environments are not identical from place to place. Some halos are torqued early and then left relatively undisturbed, while others are constantly jostled. The universe does not choose one direction for rotation, because it never had a single, global axis to begin with. Dark matter halos are the first stable containers for this angular momentum, and they dominate the mass budget. Dark matter collapses early because it does not feel radiation pressure, and it barely collides, so it can clump efficiently. It forms a virialized halo with a characteristic size and velocity scale, often described by a virial radius and virial speed. Inside that halo, angular momentum is stored in the orbital motions of many particles, not in a solid body spin. The halo spin is not a rigid body rotation, and that distinction matters for intuition. Particles move on a wide range of eccentric tilted orbits, crossing and recrossing the halo like bees in a swarm. The spin is a statistical preference in those orbits, enough to define a net L when you sum everything. It is an emergent property, not a mechanical rotation like a wheel. Cosmologists summarize halo rotation with a dimensionless spin parameter, usually written as L. It compares a halo's angular momentum to the amount needed for full rotational support, which would be enough to hold it up against gravity. Different definitions exist, and the details vary with how one measures energy or circular velocity, but the meaning is consistent. L tells you whether rotation is a minor detail or a structural constraint, and it does so without units. In simulations, L typically clusters around a few percent, often near 0.03 to 0.05, with a broad log-normal spread. That spread is a fingerprint of stochastic growth, because many small random contributions tend to produce log-normal distributions. A halo with L near the peak is common, but halos with much lower or higher values are not rare. The distribution is telling us that spin is typical, yet its exact amount is contingent. Those numbers sound small, but they are decisive for what baryons can become. A halo with L in that range is not held up by rotation alone, so gravity still dominates the overall binding. The halo remains roughly spheroidal, because random motions and anisotropic orbits provide most of the support. Yet that modest angular momentum sets a preferred plane for cooling gas, and it sets a characteristic disk size once the gas settles. It also sets a timescale problem, which is easy to miss when focusing only on shapes. Gas can lose energy quickly by radiating, but it cannot lose angular momentum as easily, because that requires torques or transport. So the gas may want to fall straight in, yet it is forced to circle, waiting for a way to redistribute L. This delay is not a footnote. It helps determine when and where stars can form. Here the narrative shifts from invisible scaffolding to visible structure, from dark halos to luminous galaxies. Baryonic gas falls into the halo's potential well and shocks near the virial radius, where infall speeds become supersonic. A shock converts ordered infall into heat, raising the gas temperature to the virial temperature, often millions of degrees in large halos. Hot gas glows in X-rays, and in clusters we can actually see this reservoir as a diffuse luminous atmosphere. The gas can radiate energy away through atomic lines, molecules, and later dust emission, depending on temperature and composition. At high temperatures, ions like oxygen, neon, and iron emit characteristic lines, turning thermal energy into escaping photons. At lower temperatures, hydrogen and helium lines matter, and molecules become important in denser, cooler regions. Energy loss allows the gas to sink deeper, but angular momentum prevents a straight collapse, and that barrier is fundamental. The gas must conserve L unless torques or outflows remove it, and that unless carries much of galaxy formation's complexity. As the gas cools, it contracts and spins up, just like the earlier cloud, because the same equation still holds. Random motions damp through collisions, and the gas becomes more ordered, with velocities aligning into a coherent rotation. The lowest energy configuration at fixed angular momentum is not a sphere, and the reason is mechanical as much as geometric. It is a flattened, rotating disk, where centrifugal support balances gravity in the plane, and pressure helps vertically. In a disk, gravity pulls inward, while rotation provides an outward effective force that can support circular motion. The balance is not perfect everywhere, and disks can be turbulent, but the overall structure is stable. The disk is gravity's compromise with conservation, a shape forced by bookkeeping rather than aesthetic design. This is why disks form rather than luminous spheres when angular momentum is significant. A sphere would require the gas to shed most of its L, because a compact sphere cannot store much angular momentum without spinning extremely fast. Shedding L is possible, but it demands a mechanism like gravitational torques, viscosity, magnetic stresses, or winds. Without strong L loss, the gas cannot reach the center efficiently, so it piles up at radii where its specific angular momentum matches circular orbits. Specific angular momentum is the per-mass version of the same idea, and it is often the more practical quantity. If a parcel of gas has a certain J, it wants to orbit at a radius where J matches the circular orbit requirement. As cooling proceeds, many parcels settle into a range of radii, building an extended disk rather than a point-like collapse. The disk's radial structure is, in part, a map of how J is distributed in the infalling gas. In the simplest picture, the gas keeps the halo's specific angular momentum and maps it into a disk. Disk scale length then tracks L times the halo's virial radius, which gives a clean, testable scaling. That link is one of the quiet successes of modern galaxy formation theory, because it connects dark matter statistics to visible sizes. It explains why disk sizes correlate with halo properties across cosmic time, even as galaxies evolve and interact. It also explains why disks are common, even though the universe is violent, and that is not a trivial point. If rotation were rare, disks would be rare, and galaxies might look more like random blobs of stars. Instead, the sky is full of flattened systems with coherent rotation, implying that angular momentum acquisition is routine. The cosmic web does not merely build mass, it builds organized motion. But the simplest picture is never the whole story, and the deviations are where the drama lives. Gas can exchange angular momentum with dark matter through torques and dynamical friction, especially when dense clumps orbit within the halo. A massive clump experiences a gravitational wake, and that wake drags on it, transferring orbital angular momentum to the surrounding matter. Over time, this can move low angular momentum material inward and push higher angular momentum material outward. Within the disk itself, structure becomes a machine for moving L around. Bars and spiral patterns can move angular momentum outward within the disk, acting like gravitational conveyor belts. gas can lose angular momentum to these patterns and drift inward, feeding central star formation or building a bulge. At the same time, the outer disk can gain angular momentum and expand, creating extended, faint outskirts. Feedback from stars and black holes can also reshape the angular momentum budget without breaking the central rule. If supernovae drive winds, those winds can preferentially remove low angular momentum gas near the centre, because that gas is densest and easiest to heat. Removing it changes what remains, often leaving behind gas with higher average J that forms a more extended disk. The galaxy's final structure becomes a record of both conservation and selective loss. Tidal torque theory also predicts variability, and observations confirm it in the diversity of galaxies. Not every galaxy is a neat spiral with a stable axis, and even spirals can be warped or lopsided. Some halos have low L and form compact, dispersion-dominated systems, where random stellar motions matter more than rotation. Some have high L and form extended, low-surface brightness disks, where stars are spread thin across large radii. The distribution of L becomes a distribution of morphologies, filtered through cooling, feedback, and environment. This is not a single parameter story, but L is a powerful first handle on why shapes differ. A small change in angular momentum can shift where gas settles, how dense it becomes, and how quickly it forms stars. In that sense, spin is not just motion, it is a control knob for visibility. Now the story confronts a question that the night sky keeps asking, especially when we map galaxies across vast volumes. If the same physics operates everywhere, why doesn't everything spin the same way? And why isn't there a universal alignment? Why aren't galaxy spins lined up like compass needles across the universe, pointing to some hidden axis? The answer is that angular momentum is a vector, and the web is not symmetric, so direction is contingent. Local tidal fields differ, accretion directions change, and mergers rewrite histories, sometimes abruptly. Even if two halos have similar masses, their neighbourhoods can be different in density, shape, and timing. A halo near a massive neighbour can be torqued strongly, while a more isolated halo evolves gently. So alignment can exist on some scales, yet it is never absolute, and it is always noisy. Environment matters first, because the web sets preferred inflow directions, and those directions can persist for billions of years. Halos fed by a dominant filament can develop spins aligned with that filament, because the inflow carries coherent orbital angular momentum. Halos at nodes can be torqued by multiple filaments, producing more complex orientations that can drift over time. Even within the same filament, neighbouring halos can end up anti-aligned, because small differences in infold geometry can flip the net vector. The web imprints correlations, but it also injects scatter, and that duality is essential. If there were no correlations, the universe would look like pure randomness, with no memory of large-scale structure. If there were no scatter, the universe would look engineered, with spins too neatly organised to be plausible. Instead, we see hints of alignment mixed with abundant exceptions, which is exactly what tidal torques predict. Merger history matters next, because mergers are angular momentum exchanges on fast timescales, relative to slow accretion. When two halos approach, their orbital angular momentum can be enormous, because the lever arm is large and the masses are huge. During the merger, some of that orbital L becomes internal spin in the remnant, and some becomes random motion. Some is carried away by ejected material and tidal debris, long streams of stars and gas flung outward like cosmic ribbons. The remnant spin axis can flip, precess, or even reverse relative to its earlier orientation, and the change can be sudden. A disk can be tilted by a minor merger, and a major merger can destroy a disk and rebuild something new. Even when a disk survives, the halo's angular momentum vector can shift and the disk may slowly realign. So the direction of a galaxy's spin is often a history, not a permanent trait. This is where counter-rotation becomes possible, and sometimes inevitable in a universe built by layered infall. A galaxy can accrete gas from a filament whose angular momentum opposes the existing disk, and the new gas may settle into a reversed plane. It can capture a satellite whose gas settles in the opposite direction, while the satellite's stars retain their original motion. It can undergo a merger that leaves stars rotating one way and gas another, producing a system with two competing clocks. Counter-rotating disks and kinematically decoupled cores are not exotic exceptions, and they are not mere curiosities. They are fossils of stochastic torques and late infell, preserved because angular momentum is hard to erase once it is organised. When we observe such systems, we are seeing the record of vector addition written into stellar orbits. The galaxy becomes a palimpsest, with older rotations partially overwritten by newer ones. Stochastic is the key word, because the universe builds hierarchically, assembling large structures from smaller ones. Small halos form first, then merge into larger halos, then accrete more, and each step brings new angular momentum vectors. Those vectors must be added, subtracted, and redistributed, and the result depends on timing as much as magnitude. The final spin is not a single inheritance, and it is not a simple average. It is an accumulated record of many interactions, written into a net axis that can be stable or fragile. A stable axis can persist when accretion is coherent and mergers are gentle, allowing the disk to maintain orientation. A fragile axis can wobble when infall directions vary, or when satellites arrive from different planes. So a galaxy's spin is both a property and a vulnerability, a strength and a potential fault line. At this point, the chapter returns to the central question with sharper tools and a more disciplined sense of cause. Why does the universe produce spin at every scale, from dust grains to galaxies and black holes, even when it starts nearly curl-free? The answer is not that the universe began as a giant rotating object, and it is not that rotation is imposed from outside. The answer is that gravity acting on imperfection produces torques, and collapse amplifies the results, turning small asymmetries into dominant motion. Spin is the memory of asymmetry, preserved because it is hard to erase, and that hardness is physical. To remove angular momentum, you must export it, either by throwing mass outward or by transferring it to something else. In an isolated system, there is no external sink, so internal redistribution becomes the only option. That is why disks form, why bars matter, and why outflows can reshape galaxies without violating conservation. Yet the story cannot settle into comfort, because gravity is double-edged. The same hierarchical growth that generates spin also threatens to destroy order, and it does so in many ways. Collisions heat disks, mergers thicken them, and tidal encounters warp them, leaving scars in stellar distributions. Angular momentum can be redistributed, but it can also be scrambled, converting orderly rotation into random motion. A delicate rotating disk looks like something that should not survive a violent universe, and that tension is real. If galaxies are continually bombarded by satellites and shaken by tidal fields, why do thin disks exist at all? When we see a grand design spiral, with crisp arms and a thin plane, we are seeing a structure that has avoided catastrophe. So survival becomes part of the mystery, not just formation. This tension is not a side note, and it drives the next act of the narrative. Disks survive when they avoid major mergers for long periods, because major mergers can transform rotation into dispersion quickly. They survive when gas keeps cooling and regrowing a thin component after heating events, like a wound that heals by slow accretion. They survive when feedback regulates star formation, preventing catastrophic central collapse that would drain angular momentum inward. Survival is a balance between acquisition and loss, between torque and dissipation, and the balance is dynamic. A galaxy can lose angular momentum from its inner gas while gaining it in the outskirts, spreading even as it concentrates. It can rebuild a disk after a merger if fresh, high angular momentum gas continues to arrive along filaments. So even stability is not static. It is a maintained state paid for by ongoing inflow and regulation. Even in survival, the accounting remains strict, and the visible consequences are everywhere in galaxy structure. If a disk stays thin, it must keep much of its angular momentum in ordered rotation, because random motion would puff it up. If it loses angular momentum, gas flows inward and builds bulges, raising central densities and changing the galaxy's profile. If it gains angular momentum, it can spread outward and form extended outer disks, sometimes faint and fragile at the edges. The visible shape of a galaxy is a map of where angular momentum ended up, and that map can be read. A prominent bulge suggests substantial inward transport or early low-J gas, while a large disk suggests sustained high-J accretion. Warps hint at misaligned infill, and thick disks hint at heating events that increased vertical motions. Even the distribution of star ages across a disk can reflect when and where angular momentum was available. The chapter also reframes collapse as a universal spin amplifier, not just a galaxy story, and that universality is striking. Any contracting system with non-zero L will spin up as its size shrinks, whether it is a halo, a cloud, or a core. That includes molecular clouds, protostellar cores, and the disks that form around young stars, where rotation becomes directly observable. It includes compact remnants, where collapse can raise all by orders of magnitude, producing rapid pulsars and spinning black holes. The same rule that shapes galaxies also shapes the objects inside them, and that continuity is the bridge ahead. A molecular cloud can fragment, and each fragment inherits some angular momentum from the larger scale flow. As the fragment collapses, it spins faster, and a circumstellar disk forms for the same reason a galactic disk forms. The scales differ by many orders of magnitude, yet the logic is unchanged, and that is one of physics' quiet unifications. This is the bridge to the intimate scales that follow. On galactic scales, angular momentum is generated by tidal torques and cosmic inflows, and it is stored in halos and disks. On stellar and planetary scales, angular momentum becomes a problem that must be solved, because too much spin prevents collapse. Stars must shed enormous amounts of L to form at all, and the mechanisms for that shedding become central to the story. Planets must assemble from disks without being flung apart by excess rotation, and that requirement shapes their architectures. A protoplanetary disk is a reservoir of angular momentum, and planets are built by moving mass through that reservoir. Some angular momentum is carried outward, some inward, and some is locked into orbital motion that can persist for billions of years. So the same conservation law that builds disks also constrains what can condense within them. They look different, but physics links them. The cosmic web torques a halo, the halo sets a disk, and the disk becomes the birthplace of smaller rotators, nested like gears. The universe keeps turning because collapse keeps concentrating motion, and because asymmetry is never fully erased. The mystery shifts from whether spin appears to how systems manage it, and how they avoid self-destruction. So Chapter 3 ends with a question sharpened by scale and by the double-edged nature of gravity. If gravity and asymmetry generate spin so reliably, why are stable rotators not shredded by the same forces that created them? How do stars form without spinning themselves apart? And how do they export angular momentum while still gathering mass? How do planets emerge from a disk that is already a reservoir of angular momentum without being scattered into chaos? The next chapter moves from galaxies to nurseries, where spin becomes unavoidable and problematic. The camera will leave the cosmic web's vast architecture and descend into cold, dark clouds threaded with turbulence. There, conservation is still the rule, but the solutions become more intricate, and the stakes become immediate. In the smallest cradles of light, the universe will again reveal its trick. Rotation is easy to create and hard to tame. We have followed spin from cosmic imperfections into rotating halos and galactic disks, watching smaller symmetries grow into organized motion. Now we drop into star nurseries, where the same rule becomes a crisis. The scale shrinks, the densities climb, and the bookkeeping becomes unforgiving, because a forming star must lose almost everything it starts with. A molecular cloud is cold, dusty, and mostly empty by Earth standards, yet it can still weigh tens of thousands of suns. Typical temperatures hover around 10 Kelvin, so cold that even simple molecules move sluggishly. In visible light, the cloud is nearly invisible, but in the infrared and radio, it becomes textured and alive. Dark lanes of dust cut across starlight like ink, while faint emission from carbon monoxide traces the gas that our eyes cannot see. The cloud is not a uniform fog. It is a hierarchy of filaments, knots, and clumps, shaped by turbulence and threaded by magnetic fields. Supersonic motions, often a few tenths to a few kilometers per second, create shocks that compress gas into denser ridges. Those ridges can be tens of light years long, and they often intersect at hubs where gravity gains its first foothold. By the time a core becomes visible as a cold, compact condensation, it is already a product of chaotic flows. Even then, the cloud is only barely bound by gravity. Thermal pressure, turbulent pressure, and magnetic support all push back against collapse. Astronomers often describe this balance with the virial theorem, which relates kinetic energy and gravitational binding energy. In plain terms, the cloud is a tug-of-war between inward weight and outward agitation. Many regions hover near the edge, where a small change can tip the outcome. Inside, turbulence creates density peaks that can collapse into protostars, and the densest peaks cool efficiently by radiating in molecular lines. When cooling is effective, pressure cannot rise fast enough to halt contraction, so gravity gains a decisive advantage. The gas begins with tiny rotation, often just a slight velocity gradient across the cloud. That gradient can come from shear in the larger cloud, from colliding flows, or from the residual vorticity of turbulence. Tiny does not mean harmless, because collapse is an amplifier. As radius shrinks, moment of inertia falls, and angular speed must rise. The basic relation is simple. For a given mass element, angular momentum is roughly mass times radius times tangential speed. If the radius drops by a factor of 1,000,000, the rotation rate can rise by a factor of 1,000,000,000,000, unless something intervenes. This is why a barely measurable twist in a cold core can become a dominating force near the centre. If angular momentum were perfectly conserved in each collapsing parcel, the spin-up would be extreme. The inward fall would hit a centrifugal barrier long before reaching stellar densities. Matter would begin to orbit rather than plunge, and the collapse would stall at a radius set by its specific angular momentum. Instead of a compact star, you would expect a broad, rotating structure that cannot shed its spin. This is the angular momentum problem of star formation. Gravity wants to concentrate mass, yet rotation resists concentration with increasing strength. The resistance is not mysterious. It is the same outward centrifugal effect that keeps planets in orbit. As the gas contracts, the centrifugal term grows faster than gravity for a given parcel, because rotation speeds up so rapidly. The closer you get to the centre, the more rotation insists on being heard. A simple estimate makes the paradox concrete, and it is worth lingering on because the numbers are so stark. Take a core with a small initial specific angular momentum and shrink it by many orders of magnitude. Observed dense cores often have specific angular momenta around 1021 to 1022 centimeters squared per second, values that sound abstract until you propagate them inward. If you conserve that quantity all the way to stellar radii, the implied spin becomes physically impossible. The implied rotation rate becomes so large that centrifugal support balances gravity at a radius far larger than a star. Collapse should stall into a ring, not a sun. In other words, the gas should settle into orbit before it ever reaches the densities needed for hydrogen fusion. The paradox is not subtle. It is a direct contradiction between naive conservation and the existence of stars. The universe, however, is full of stars, so conservation must be honoured in a more global way. Yet stars form everywhere in the Milky Way, and they form efficiently enough to light galaxies. In giant molecular complexes, clusters of newborn stars appear in bursts, and the surrounding gas is reshaped by their feedback. Even in quieter regions like Taurus, low-mass stars emerge steadily from cold filaments. Nature must move angular momentum out of the way. The only question is how many channels it uses and how they cooperate. The first escape route is geometric and unavoidable. Infall with non-zero angular momentum cannot go straight to the centre, so it spreads into a disk. As gas falls inward, it conserves angular momentum by increasing tangential speed, and that speed creates a preferred plane. Collisions and shocks between streams dissipate vertical motion so the flow flattens. What begins as a three-dimensional collapse becomes a two-dimensional structure with a bright, rotating mid-plane. A protostellar accretion disk is not a side effect. It is angular momentum storage, a reservoir that lets mass keep falling without violating conservation. In images from facilities like ALMA, these disks appear as compact, dusty pancakes, sometimes with rings and gaps already etched into them. In scattered light, the disk surface glows like a thin mist, while the midplane remains dark and opaque. Visually, it is the moment when collapse becomes architecture, but a disk alone does not solve the problem, because gas still must move inward through the disk. Inward motion requires outward angular momentum transport. If every ring of gas kept its angular momentum, it would stay on its orbit forever, like a planet that never migrates. Accretion is therefore not just about gravity pulling inward. It is about some mechanism providing a torque, a way to change orbital angular momentum over time. The key idea is simple bookkeeping. If a ring of gas loses angular momentum, it can drop to a smaller orbit. The lost angular momentum must go somewhere else. It can be handed to neighbouring rings, carried by waves, or exported by magnetic stresses. The disk, in effect, must act like a machine that moves angular momentum outward while letting mass leak inward. In a purely laminar disk, transport is too slow. Molecular viscosity is tiny, and the disk would accrete on timescales longer than observed. Gas molecules do collide, but the mean free paths and thermal speeds are not enough to generate strong friction across astronomical distances. If you relied on microscopic viscosity alone, the disk would persist for far longer than the few million years typical of protoplanetary disks. Observations force us to conclude that something acts like a much larger effective viscosity. So disks need an effective viscosity, produced by turbulence and stresses that act like friction. The disk becomes an angular momentum conveyor belt. Astronomers often capture this with the alpha disk idea, where turbulent stresses scale with pressure, but the deeper point is physical rather than parametric. The disk must contain correlated motions, eddies, waves, magnetic tensions that systematically transport angular momentum outward. Random stirring is not enough unless it produces a net torque. Turbulence can be driven by several processes, including gravitational instability in massive disks. If the disk is heavy enough relative to the star, its self-gravity can amplify small density perturbations into spiral arms. Those spirals are not merely visual features, they exert gravitational torques that exchange angular momentum between radii, and they can drive shocks that dissipate energy. In the earliest, most massive phases, this route can be especially important, yet the most famous driver begins with a weak magnetic field. Even a tenuous field, frozen into a partially ionized plasma, can link different parts of the disk. The key is that disks are not perfect neutral gases. Cosmic rays, X-rays from the young star, and radioactive decay can ionize a fraction of the material, and that fraction can be enough for magnetic coupling in some regions. Where coupling is strong, magnetism becomes a lever arm. The magnetorotational instability turns gentle magnetism into vigorous mixing. It works because disks rotate differentially, with inner orbits moving faster than outer ones. Differential rotation means shear, and shear contains free energy. The inner disk wants to lap the outer disk, and magnetic field lines can transmit that tendency as a stress. The instability is a way for the disk to tap its own shear and convert it into turbulence. Imagine two neighbouring fluid layers connected by a magnetic field line. Magnetic tension acts like a spring, resisting their relative motion. If the inner layer moves ahead, it stretches the field line and pulls on the outer layer. That pull is not a metaphor. It is a real Lorentz force acting on charged particles, which then drag neutrals along through collisions. The field line becomes a tether that couples their fates. The inner layer drags the field forward and pulls the outer layer ahead. The outer layer gains angular momentum and moves outward. This outward motion is crucial because it is where the angular momentum goes. At the same time, the inner layer feels an equal and opposite tug. It loses angular momentum and can no longer maintain its orbit at the same radius. The inner layer loses angular momentum and spirals inward, releasing gravitational energy as heat and radiation. The instability feeds on shear, so it sustains turbulence. As turbulence grows, it tangles magnetic fields and creates fluctuating stresses that continue to move angular momentum outward. The disk brightens where energy is dissipated, and the inner regions can glow in infrared and ultraviolet. In a sense, the disk converts orbital energy into light by paying the price of angular momentum transport. MRI is powerful because it does not require a strong field. Even a weak field can couple layers, and the differential rotation supplies the energy. The remarkable part is that the disk's own rotation, which initially blocks collapse, becomes the fuel for the process that unlocks collapse. There are complications. Regions of low ionization can weaken MRI, and dust can soak up charges. But the core intuition remains robust. Magnetism turns shear into torque. This is one of the chapter's central reversals. The same rotation that blocks collapse also creates shear that enables angular momentum transport. The obstacle becomes the engine. The disk is not fighting rotation so much as using rotation against itself, converting ordered motion into turbulent stresses that rearrange the flow. It is a subtle kind of self-rescue, written into the equations of magnetized fluids. Disks also move angular momentum through spiral density waves and shocks. In young disks, self-gravity can form spirals that torque the gas. Even in less massive disks, planets or companions can excite waves that carry angular momentum as they propagate. Where those waves steepen into shocks, they deposit their angular momentum and heat the gas. Visually, the disk can show grand design spirals, like miniature galaxies wrapped around a forming star. All of these mechanisms share one outcome. Mass flows inward, angular momentum flows outward, and the disk spreads while the star grows. The outer disk can expand to hundreds of astronomical units, while the inner disk drains onto the star. This spreading is not incidental. It is the signature of angular momentum conservation working on a system with internal torques. You can almost picture the disk as a figure skater, extending one arm while pulling the other inward. Still, the disk cannot keep all the angular momentum forever. If the system kept every bit of its original angular momentum, the newborn star would spin too fast. A star has a small radius compared to the original core, so it cannot store much angular momentum without approaching breakup speed. Breakup is the point where centrifugal force at the equator matches gravity, and material would be flung off. The fact that most young stars rotate well below breakup tells us that additional removal is happening, so star formation needs a second escape route that is more dramatic. It must eject angular momentum into space. This is where the story becomes cinematic, because the solution is not purely internal redistribution. The forming system opens a channel that throws matter outward, carrying angular momentum like a discarded scaffold. The collapse does not merely settle, it launches. Protostellar jets and outflows provide that route. They are launched from the inner disk and star disk interface, where magnetic fields are strongest. The inner few astronomical units are a region of intense gradients. Temperature, density, ionization, and magnetic pressure all change rapidly. Accretion funnels material inward, and some fraction is redirected upward along magnetic field lines. The result is a bipolar structure, because the disk has two faces and the field has two open directions. Magnetic fields thread the rotating disk like wires. As the disk turns, field lines twist, building magnetic pressure and tension. The twist stores energy in the magnetic field, and the field reacts by trying to straighten. That reaction can accelerate plasma along the field, away from the disk surface. In idealized models, the field lines act like rigid rails, and the rotation provides the push. Along open field lines, gas can be flung outward magnetocentrifugally. The outflow carries away angular momentum, letting inner material accrete. The phrase magnetocentrifugal captures the hybrid nature of the launch. Centrifugal force helps lift the gas, while magnetic tension guides and collimates it. As the gas moves outward, it can carry not only mass but also the rotational imprint of the disk. The outflow is, in a sense, the disk's spin made visible. Jets are narrow and fast, while molecular outflows are wider and slower. Together, they remove both mass and angular momentum from the forming system. Jets can reach hundreds of kilometers per second, punching through the surrounding cloud like needles of light. Molecular outflows, traced by CO emission, form broad lobes that sweep up ambient gas. In images, you often see a dark core with two opposing cavities, as if the star is exhaling along its rotation axis. Observations show the signatures clearly. Bipolar outflows carve cavities in surrounding clouds, and jets terminate in bright shocks. The cavities can be outlined by scattered infrared light, revealing curved walls where dust has been cleared. Along the jet axis, knots appear where the flow varies in time, producing internal shocks. Each knot is a timestamp, a record of episodic accretion and ejection. Herbig, Hero objects mark those shocks, glowing where supersonic jets slam into ambient gas. They are signposts of angular momentum loss in action. In optical images, they appear as small, luminous bow shocks with delicate filaments, often tinted by emission lines from oxygen, sulfur, and hydrogen. The physics is violent but precise. Kinetic energy becomes heat, atoms are excited, and the gas radiates as it cools. The jet's momentum is written into the shape of the shock front. This is not a minor correction to the collapse picture. Outflows can regulate accretion rates and set the final stellar mass. If too much mass were allowed to fall in unimpeded, stars would grow larger than we observe, and the initial mass function would look different. Outflows provide a feedback valve, removing material and injecting turbulence. They can even help determine how long the disk survives by dispersing nearby gas. They also connect star formation to the larger cloud. By injecting momentum and turbulence, outflows can stir the environment and influence nearby collapses. A cluster-forming clump becomes a network of interacting outflows, where one newborn star can compress gas in one direction and evacuate it in another. This makes star formation a collective phenomenon rather than a set of isolated events. The angular momentum problem, therefore, is not confined to one star's disk. It shapes the ecology of an entire region. Even with disks and jets, another pathway often resolves the angular momentum budget. The cloud can fragment and form multiple stars. Fragmentation is encouraged by turbulence, and by the fact that collapsing gas can break into pieces when it cannot maintain pressure support. As density rises, the gas can become optically thick and heat up, which resist fragmentation, but before that stage there is ample opportunity. The outcome is often a small family rather than a single child. Fragmentation turns spin into orbit. Instead of one object holding all the angular momentum as rotation, two or more objects can store it as orbital motion. Orbital angular momentum can be enormous compared to what a single star can hold as spin, because the lever arm, the separation, can be large. A wide binary can carry the parent core's angular momentum without any component rotating dangerously fast. The system keeps the angular momentum, but it distributes it into a safer form. This is why binaries are common, especially among massive stars. A significant fraction of stars are born in pairs or higher multiples. For massive stars, multiplicity fractions are particularly high, suggesting that fragmentation and subsequent dynamical capture are integral to their formation. Even among Sun-like stars, binaries and triples are not rare, and their orbital properties carry clues about the angular momentum of their natal cores. When you see a binary, you are seeing an angular momentum solution written in gravity. In a binary, angular momentum is not trapped inside a single spinning body. It can live in the separation and the orbital period. The orbit can also exchange angular momentum with surrounding disks through resonant torques, shaping gaps and streams. Circumbinary disks can feed material inward through complex flows, while circumstellar disks around each component can be truncated and warped. The geometry becomes intricate, but the accounting remains the same. Interactions then redistribute angular momentum further. Disks around each component can exchange torques with the binary orbit, moving angular momentum outward. In a young cluster, close encounters can harden binaries, eject companions, and reshape orbits. A triple system can be unstable, flinging one star outward while tightening the remaining pair. The angular momentum problem becomes a dynamical ecosystem, with exchanges that resemble gravitational billiards. So the paradox has multiple solutions working at once. Disks store angular momentum, turbulence transports it, jets expel it, and fragmentation converts it into orbits. These channels do not operate in isolation, and their relative importance changes with time. Early on, infall and disk formation dominate. Later, jets and winds can regulate the system, while companions and cluster dynamics can rewrite the distribution. The result is not a single pathway, but a family of pathways that converge on the same necessity. The deeper mystery is that these solutions do more than permit starbirth. They create the conditions for planet formation. The same disk that acts as an angular momentum reservoir also becomes a chemical laboratory and a construction site. It sets the temperature gradient that determines where ices can exist, and it controls how solids drift and concentrate. The angular momentum problem, solved for the star, leaves behind a rotating stage for worlds. A protoplanetary disk is a leftover of the angular momentum budget. It is the material that could not fall straight in, and it becomes a construction site. The disk's midplane is dense and shielded, while its surface is irradiated by the young star's ultraviolet and X-rays. In that layered structure, chemistry diverges, and dust grains acquire icy mantles beyond the snow lines. The disk is both a dynamical system and a stratified environment. In the disk, dust grains collide and stick, growing from micron sizes to pebbles. Gas drag and turbulence control their relative speeds and settling. At first, electrostatic forces and sticky ices help grains adhere, forming fluffy aggregates. As they grow, collisions become faster and more destructive, creating barriers like bouncing and fragmentation. The question becomes whether growth can outrun the processes that grind solids back down. As solids grow, they drift inward because of headwind from slightly sub-Keplerian gas. This drift is fast enough to threaten growth, so another instability helps. Gas pressure provides partial support against gravity, so gas orbits slightly slower than the Keplerian speed. Solids, which want to orbit faster, feel a headwind that robs them of angular momentum. They spiral inward, sometimes on timescales of only thousands of years at certain sizes, which is alarmingly short. The streaming instability concentrates pebbles by feedback between solids and gas. Dense clumps can collapse gravitationally into planetesimals. The mechanism is subtle, As pebbles drift, they drag gas with them, altering the local gas velocity and creating regions where more pebbles pile up. This positive feedback can produce dense filaments of solids, and once the density is high enough, self-gravity takes over. In visual terms, a smooth disk suddenly develops streaks and knots, like traffic jams forming on a highway. Planetesimals then collide and accrete into protoplanets, while gas can be captured to form giant planet envelopes. The disk's angular momentum shapes every step. Collisions are not random in a vacuum. They occur in a rotating frame with shear, resonances, and gas drag. Growing bodies stir their surroundings, increasing relative velocities and changing collision outcomes. The disk's rotation sets the baseline from which all these interactions depart. Planets inherit angular momentum mostly as orbital motion, not spin. Their orbits are the disk's rotation made durable. A planet's spin is important for its day length and climate, but its orbital angular momentum is typically far larger. This is why the architecture of a planetary system is primarily an angular momentum architecture. The disk's rotation becomes a set of stable paths, and those paths become the skeleton of a system. This explains a basic architectural fact. Planets in a system usually orbit in roughly the same plane and the same direction. The reason is not coincidence, but the flattening of the disk under rotation and pressure. Collisions and gas drag damp inclinations, pulling solids toward the midplane. Over time, the disk becomes a thin, rotating sheet, and planets assembled within it inherit that geometry. Coplanarity is the disk's memory. The disk is flattened by rotation and pressure, so it imposes a shared plane on what condenses within it. When we look at the solar system, the near alignment of planetary orbits is a fossil of the Sun's accretion disk. Even the small deviations, the slight tilts and eccentricities, become clues about later perturbations. The disk writes the first draft and subsequent dynamics edit it. But the architecture is not frozen at birth. Migration moves planets through the disk by exchanging angular momentum with gas. A planet's gravity excites spiral density waves in the disk, and those waves carry angular momentum away. Depending on where the waves damp, the planet can lose or gain angular momentum and shift its orbit. Migration is therefore another chapter of angular momentum transport, now mediated by a planet rather than by turbulence alone. Type 1 migration affects lower mass planets through spiral wakes. Type 2 migration affects gap-opening giants that couple to disk evolution. In Type 1, the planet is embedded in the gas, and the torques can be strong enough to move it inward quickly. In Type 2, a massive planet clears a gap and migrates more slowly, roughly following the disk's viscous evolution. The details depend on disk temperature, density, and turbulence, but the theme is consistent. Angular momentum exchange drives motion. Resonances can lock planets into period ratios, pumping eccentricities and inclinations. Later scattering can break resonances and rearrange spacing. When two planets migrate, they can become trapped in mean motion resonance, where their gravitational tugs repeat in a regular pattern. This can stabilize or destabilize the system depending on damping and mass ratios. If the gas dissipates and damping weakens, resonant chains can unravel, leading to close encounters and orbital reshuffling. Some systems show the exceptions that sharpen the mystery. Hot Jupiters likely formed farther out and migrated inward, ending up on short-period orbits. Their existence tells us that angular momentum can be redistributed dramatically after formation. A giant planet cannot form easily in the hot inner disk, so it must have moved. The question becomes what mechanism dominated: disk-driven migration, high eccentricity tidal migration, or a combination. Some hot Jupiters are misaligned with their star's spin axis, implying disk tilts, dynamical interactions, or later perturbations. Misalignment is measured through techniques like the Rossiter-McLaughlin effect, where a transiting planet blocks part of a rotating stellar surface and distorts spectral lines. The observation is geometric, but the implication is dynamical. Something caused the orbital plane to tilt relative to the stellar equator, and that something involved angular momentum exchange. Misalignments can arise if the disk itself is torqued by a companion star or by chaotic infall. They can also arise from planet-planet scattering and Kozai cycles. A distant companion can induce oscillations in inclination and eccentricity, trading one for the other over long timescales. Scattering can throw planets onto tilted orbits, and tides can later circularize them close to the star. The resulting system looks calm, but its angular momentum history is turbulent. So even when the disk begins orderly, later dynamics can rewrite the angular momentum distribution. The system keeps evolving its spin story. The disk phase lasts only a few million years, but the consequences can persist for billions. Orbits can be sculpted by resonances, altered by encounters, and damped by tides. Angular momentum remains conserved overall, yet it is constantly repackaged into new forms. The star's own rotation also refuses to stay fixed. Accretion can spin a protostar up, while magnetic coupling to the disk can break it. As material falls along magnetic field lines, it can deliver angular momentum to the star. At the same time, the magnetic connection between star and disk can act like a brake, transferring angular momentum back to the disk or into winds. This interplay helps explain why many young stars rotate more slowly than simple accretion would predict. After the disk disperses, stellar winds carry away angular momentum over billions of years. Magnetic braking slows many stars as they age. The wind is a stream of charged particles tied to magnetic field lines, and those field lines enforce corrotation out to large distances. That lever arm allows the wind to remove substantial angular momentum. The result is a gradual spin down, which is why older sun-like stars tend to rotate more slowly than younger ones. Tides then become important in close systems. Tidal friction transfers angular momentum between spins and orbits, synchronizing rotations and circularizing orbits. Tides arise because gravity stretches bodies, and internal friction dissipates the energy of that deformation. Over time, the system evolves towards states of lower energy at fixed angular momentum, often locking rotations and shrinking or circularizing orbits. The process is slow but relentless, and it can dominate the long-term evolution of close-in planets. On planets, tides can lock rotation, as with the Moon's synchronous spin. They can also heat interiors and reshape climates. Tidal heating can keep subsurface oceans liquid or drive volcanism, depending on orbital eccentricity and internal structure. The same mechanism that slows rotation can power geology. Angular momentum exchange, therefore, is not only about orbital geometry. It can determine whether a world is inert or active. Impacts add another layer of contingency. Giant collisions can tilt spin axes, change rotation rates, and strip atmospheres. In the chaotic late stages of planet formation, bodies collide at high speeds, and the angular momentum of the impact can dominate the outcome. A glancing blow can spin a planet up and tilt it, while a head-on collision can merge and reset the rotation. Each impact is a localized violation of gentleness, and the resulting spin state is a record of that violence. Earth's obliquity and the Moon's existence point to a violent angular momentum exchange early in our history. Rotation records those accidents. The leading hypothesis for the Moon's origin involves a giant impact that placed debris into orbit, which then accreted into the Moon. That event redistributed angular momentum between Earth's spin and the Earth, Moon orbit. The present system still evolves as tides transfer angular momentum outward, slowly pushing the Moon away. Internal dynamics keep modifying spin as well. Differentiation, core formation, and mantle convection redistribute mass and change moments of inertia. When a planet's mass moves inward, its moment of inertia decreases, and its rotation rate can increase slightly, like a skater pulling in their arms. When mass moves outward, rotation can slow. These are modest changes compared to impacts or tides, but they matter over long timescales. Even without external torques, changing internal structure can alter rotation rate slightly. Angular momentum stays, but the spin state shifts. On Earth, for example, mass redistribution in the atmosphere and oceans causes measurable variations in day length. On stars, internal angular momentum transport can couple core and envelope, changing surface rotation as the star evolves. The principle is the same across scales. The distribution of mass controls how angular momentum manifests. So the chapter's tension persists beyond birth. Angular momentum is conserved globally, yet it is endlessly redistributed locally. The conservation law is strict, but it does not dictate where the angular momentum must reside. It can live in a disk, in a jet, in a binary orbit, or in the spin of a planet. The universe keeps the total, then improvises with the parts. This is the chapter's core theme. The physics that should prevent collapse becomes the mechanism that builds disks, binaries, and planets. Rotation is not merely a barrier, it is a sculptor, forcing matter into flattened structures, driving instabilities, and enabling the transfer processes that make compact objects possible. The very difficulty of forming a star becomes the reason a star has a disk, and the disk becomes the reason worlds can form. Gravity concentrates matter, conservation concentrates rotation, and the system must invent pathways to move angular momentum outward. Those pathways become the architecture of worlds. When we look at a planetary system, we are seeing a resolved paradox. The orbits, the spins, the tilts, and the resonances are not decorative features. They are the surviving ledger entries of angular momentum management. We return to the central question with a sharper edge. Why does the universe produce spin at every scale, and why does it keep it for so long? Part of the answer is historical. Early fluctuations and tidal torque seed angular momentum, and collapse amplifies it. Part of the answer is structural. Once angular momentum exists, it is hard to erase without a torque, and torques require interactions. The universe is not frictionless, but neither is it eager to dissipate rotation completely. The answer is not a single origin event, but a repeated pattern. Imperfection seeds angular momentum, collapse amplifies it, and transport mechanisms decide what forms. The pattern repeats from clouds to disks to planets, and it repeats again in the evolution of stars and systems. Each stage inherits a distribution of angular momentum and then reshapes it. The question is not whether angular momentum matters, but how it chooses its final hiding places. Now we pivot from birth to evolution. To understand spinning worlds and stars, we must measure rotation, track how it changes, and see what it powers. Rotation leaves signatures in spectral line broadening, in periodic brightness variations from star spots, and in the timing of pulsations. In disks, rotation is mapped through Doppler shifts across the disk face. The act of measuring spin becomes a way of reading history. Rotation is not only a constraint on formation, it becomes an energy source for magnetic storms, stellar activity, and the most extreme compact objects. A rotating magnetic field can accelerate particles, heat coronae, and drive flares. In more compact remnants, rotation can become a reservoir of staggering energy, tapped by magnetic fields and relativistic processes. The same conserved quantity that once threatened to halt collapse can later power the brightest, fastest phenomena. The next chapter follows that thread forward in time. We move from how spin is managed at birth to how spin is observed, slowed, and sometimes weaponized by physics. We will watch rotation age, and we will see how angular momentum loss becomes a clock for stars. We will also confront cases where rotation is not gently redistributed, but catastrophically released. The story of spin does not end with formation. It intensifies. The universe refuses to keep still, and star formation shows why. Spin is the obstacle that becomes the blueprint, and the blueprint keeps being revised. Every disk, every jet, every binary orbit is a compromise between gravity's desire to concentrate and angular momentum's insistence on motion. If you want to understand how worlds and stars come to be, you have to follow the spin, because it never truly goes away. Spin is not only inherited motion from formation, because spin evolves, leaks, couples, and sometimes detonates into observable consequences. If Chapter 4 showed how systems survive birth, this chapter tracks how they age, quietly at first, then with sudden, irreversible edits. The central question returns with sharper stakes, because it is no longer about origins alone. Why does the universe produce spin at every scale, and why does it keep changing? We start with measurement, because spin is usually inferred rather than seen, and inference forces us to confront what we cannot directly image. For stars, rotation hides in spectra, light curves, and subtle vibrations that ripple through their interiors like seismic waves. For planets, rotation is mapped by radar echoes and changing brightness, where surface and cloud patterns act like moving fingerprints. For pulsars, spin becomes timing, and timing becomes a ruler for extreme physics, so steady that a drifting microsecond can matter. Spectral line broadening is the workhorse for stellar rotation, and it begins with a simple fact about light and motion. A rotating photosphere Doppler shifts light from approaching and receding limbs, so one side is slightly blue shifted while the other is slightly red shifted. When those contributions blend in our telescope, the combined effect widens absorption lines in a predictable way, and the width encodes speed. The measured quantity is v sin e. the equatorial speed times the sine of inclination, because we only see the component along our line of sight. We learn speed, but geometry keeps a secret unless inclination is known, and that hidden angle can turn certainty into a range. In practice, astronomers compare observed spectra to non-rotating templates, then model how rotation smears the line profiles across the detector. Thermal broadening, pressure broadening, and turbulence also widen lines, so rotation must be separated from other sources of blur. That separation is easier in hot stars with sharp lines, and harder in cool stars where convection adds its own messy signature. Even so, the rotational imprint is distinctive, an almost sculpted widening that repeats across many lines. The method is indirect, yet it has mapped stellar spin across the Hertzsprung, Russell diagram for decades. Starspot modulation turns rotation into a clock, and it does so with a kind of accidental artistry. Dark spots and bright faculae ride across the stellar disk and modulate brightness, because magnetic regions block or enhance light as they rotate in and out of view. The period of that modulation reveals the rotation period at spot latitudes, which is why spots are both useful and tricky. Spot lifetimes and migration complicate the signal, but the periodicity is often unmistakable when the pattern persists. In active young stars, the modulation can be large and stable enough to track for years, and the light curve becomes a long strip of rotating weather. The visual is deceptively simple, a star that seems constant, then a gentle dip, then another, as if something is turning behind a veil. Yet the physics behind those dips is magnetic, not merely geometric, and magnetic regions can emerge, decay, and drift in latitude. That drift matters because many stars rotate differentially, so a spot at one latitude keeps time differently than a spot elsewhere. When multiple spots exist, their signals interfere and create beat patterns that can masquerade as changing rotation. The reward is worth the effort, because spot modulation can reveal not only a period, but a map of shear. Astrosismology adds a deeper probe, and it feels like listening rather than looking. Stars ring with acoustic and gravity modes that split under rotation, because rotation breaks the symmetry that would otherwise keep certain frequencies identical. The splitting pattern reveals internal rotation rates and radial shear, and it can show whether a core spins faster than an envelope. It can also constrain inclination when combined with mode geometry, because the visibility of different oscillation components depends on viewing angle. With enough modes, a star becomes a rotating object with layers, not a single number, and the interior stops being a black box. Historically, this was a quiet revolution, because it turned stellar evolution from a surface story into an internal one. Heliosismology first did it for the Sun, mapping rotation through much of its interior and revealing the tachocline as a thin shear layer. Space missions later extended the method to other stars, and suddenly rotation could be compared across ages and masses with new precision. The result is not always intuitive, because some stars show cores that keep spinning while envelopes break. That mismatch becomes a clue about angular momentum transport, and the clue points to magnetic fields, waves, and internal mixing. Planets require different tricks because they are faint and close, and because their surfaces are often hidden by clouds or darkness. Radar can bounce signals off nearby worlds and map rotation directly, because the returned echo carries a Doppler shift that depends on which limb is moving toward us. Doppler shifts in the returned signal reveal spin rate and even surface roughness patterns, since rough terrain scatters differently than smooth plains. For distant planets, light curves do the work, and the method becomes a kind of remote sensing by rhythm. As a planet rotates, continents, clouds, and storms change the reflected or emitted light, and the periodicity is a rotation signature filtered through weather and viewing angle. The picture here is cinematic, a dim point of light, barely separated from its star, yet its brightness rises and falls with a hidden day. The signal can be subtle, because clouds can erase surface patterns, and seasons can shift the average reflectivity. Still, repeated cycles can pull a rotation period from noise, especially when combined with colour information that hints at oceans, land, or hazes. Even when we cannot resolve a disk, rotation can still announce itself as a repeating modulation. A planet's day, in other words, can be measured from across interstellar space. Pulsars make rotation almost absurdly measurable, and they do it with a precision that feels like a dare. A neutron star beams radiation like a lighthouse, and each pulse is a tick that marks a full turn of an object only tens of kilometers wide. Timing precision can reach microseconds or better over long baselines, because radio telescopes can fold thousands of pulses into a stable profile. Spin-down rates are measured as tiny drifts in pulse period, and those drifts can be linked to magnetic torque and particle winds. Glitches appear as sudden spin-ups, revealing internal superfluid dynamics that store and release angular momentum. In pulsars, spin is not inferred from shape or spectra, because spin is the observable itself. The visual counterpart is a clean pulse train on a screen, a heartbeat of the cosmos that refuses to blur. Yet even this clock is not perfectly smooth, because timing residuals reveal companions, orbital motion, and subtle relativistic effects. Pulsars have been used to detect planets, to test general relativity, and to probe the interstellar medium through dispersion. The astonishing part is that all of this begins with rotation, because rotation provides the metronome. When the metronome stutters, the stutter becomes data. Now the story tightens around evolution. Rotation is a reservoir of angular momentum and energy, but it is not isolated, and isolation is the rarest condition in astronomy. Magnetic fields couple rotating plasma to escaping winds, so a star can torque itself through its own outflow. Tides couple a rotating body to its companion's gravity, so spin and orbit trade momentum through deforming bulges. Collisions couple spin to orbital motion in a single violent exchange, and the direction of the final spin can flip in an instant. In each case, the bookkeeping is strict, but the outcomes are diverse, because the pathways for exchange are numerous. Young stars rotate fast because they inherit angular momentum from collapsing cores and disks, and collapse is a spin amplifier. As a molecular cloud core shrinks, even a slight initial twist becomes rapid rotation, because the same angular momentum is packed into a smaller radius. Many arrive on the main sequence with periods of days, sometimes less, and their magnetic activity can be intense. Accretion can spin them up, while magnetic star disk coupling can break them early, because field lines can connect the star to the slower disk. Once disks disperse, winds take over as the long-term break, and the surface rotation becomes a record of both birth conditions and subsequent loss. This early phase is messy, and that mess is part of the point. Some young stars remain disk-locked for a time, rotating at nearly constant periods despite contraction that would otherwise spin them up. Others lose their disks quickly and accelerate, becoming rapid rotators that flare and spot heavily. Clusters show this diversity as a spread in rotation periods at the same age, as if the stars are born with different breaking histories. Over tens to hundreds of millions of years, the spread narrows and the population begins to converge. Spin evolution is therefore not just aging, but a gradual forgetting of initial conditions. Magnetic braking is the key mechanism for sun-like stars, and it is a triumph of plasma physics applied to distant objects. A stellar wind is a flow of charged particles tied to magnetic field lines, so the outflow is not free to ignore the star's rotation. Those field lines enforce corrotation out to an Alfvén radius, which acts like a lever arm where the wind's kinetic energy matches magnetic energy density. The wind carries away angular momentum far more efficiently than a simple mass loss would suggest, because the effective radius of torque is much larger than the stellar surface. The star spins down because it is effectively pushing on a long magnetic handle, and the handle reaches into space. The strength of this braking depends on magnetic field topology, mass loss rate, and rotation itself, so the process is nonlinear. Faster rotation tends to strengthen magnetic activity up to a saturation point, which can make the early braking strong. Over time, as rotation slows, magnetic fields weaken and the wind torque declines, so the braking eases. This feedback is why spin-down curves bend rather than remain straight. It also explains why two stars of similar mass can diverge if their magnetic behavior differs. The wind is invisible, yet its torque sculpts stellar lifetimes. The Schumannic law captures the broad trend, and it emerged from careful comparisons of cluster stars. For solar-type stars, rotation rate declines roughly as the inverse square root of age, a simple relation that acts like a first-order map of spin-down. It is not exact for every mass and activity level, but it is a useful concept because it links rotation, chromospheric activity, and lithium depletion in a single aging picture. Spin slows, activity declines, and magnetic heating weakens over time, so the star's high-energy environment becomes calmer. The sun's relatively slow rotation is a sign of middle age, not a birth condition, and that realization reframes our own star. Gyrochronology turns that trend into a clock, and it is a rare clock that does not rely on nuclear burning models alone. If rotation period correlates with age for a given stellar mass, then spin can date stars, especially when other age indicators are ambiguous. The method works best for cool stars with convective envelopes and well-behaved magnetic braking, where the relation between colour and period is tight. It struggles for very young stars with disk effects, and for older stars where braking may weaken, perhaps because magnetic field geometry changes. It also depends on calibration from clusters and binaries with known ages, because a clock needs a reference. Still, it is a rare tool that reads time from motion, and it turns a star's day into a measure of its life. The deeper implication is philosophical as much as practical. Rotation is not just a property, but a memory of interaction with the surrounding environment, and memory can be decoded. When gyrochronology works, it suggests that stellar evolution is not purely internal, because the exterior wind torque matters. When it fails, the failure is informative, because it points to missing physics in magnetic braking or internal transport. Either way, spin becomes a diagnostic, not merely a number in a catalogue. The universe leaves timestamps in turning. Differential rotation complicates every simple picture, because many stars do not rotate like solid spheres, and fluids rarely cooperate with simplicity. The Sun's equator rotates faster than its poles, and the shear is measurable in sunspot tracking and helioseismology. Starspot tracking reveals similar patterns in other stars, though with wide diversity in both magnitude and sign. Astroseismology can show radial differential rotation, where the core and envelope differ, and that difference can persist for long periods. Differential rotation is not a detail, because it is the raw material for dynamos, and dynamos feed back on rotation. Visually, differential rotation is a slow tearing of patterns, like ink stretched across a spinning globe. A spot at the equator drifts ahead of a spot at higher latitude, and over weeks the alignment is lost. In the Sun, this shear helps wind up magnetic fields, storing energy that can later be released as flares. In other stars, stronger shear can mean stronger cycles, though the relationship is complex. The key is that rotation is not uniform, so angular momentum is constantly being redistributed internally. The star is always negotiating with itself. Gas giants also rotate differentially, because they are fluid and stratified, and their visible atmospheres are only the top of a deep convective engine. Jupiter's clouds show bands with different rotation rates by latitude, and the contrast is obvious in time-lapse imagery, where belts and zones slide past one another. Deep interior rotation may be closer to a single rate, but the atmosphere is sheared by convection and jets that tap internal heat. Saturn shows similar banding, and its true rotation period is hard to define because the magnetic field is unusually axis-symmetric, offering few stable markers. In fluid worlds, rotation is a field, not a single number, and the day depends on depth. Convection and rotation interact through the Coriolis effect, which turns straight motion into curved paths in a rotating frame. Rotation organizes rising and sinking flows into columns and spirals, especially when rotation is fast compared to convective turnover times. The strength of that organization depends on the Rossby number, which compares inertial forces to Coriolis forces in a simple ratio. Low Rossby number means rotation dominates, and flow becomes strongly constrained, so turbulence aligns into coherent structures. High Rossby number means turbulence can ignore rotation and mix more freely, producing a different pattern of heat transport. This balance shapes differential rotation profiles and sets the stage for magnetic field generation. The visual here is almost architectural. In a rapidly rotating fluid, convection can form tall, rotating columns aligned with the spin axis, structures that look like invisible pillars supporting the flow. In slower rotation, those pillars dissolve into chaotic plumes that wander without preference. The difference is not cosmetic because it changes how angular momentum moves from equator to pole, and from deep layers to the surface. It also changes where shear concentrates, and shear is fuel for magnetic amplification. Rotation, convection, and magnetism form a three-way negotiation. Magnetic dynamos are where spin becomes an engine, and the engine runs on induction and feedback. A conducting fluid moving through a magnetic field induces electric currents, because charges are pushed by the Lorentz force as the fluid crosses field lines. Those currents generate new magnetic fields that can reinforce the original field, provided the geometry and timing cooperate. Rotation helps by organising flows and sustaining coherent shear, which keeps the induction from averaging away. Convection supplies motion, while rotation supplies structure and helicity, meaning a twist that can build large-scale order. The result is a self-excited magnetic field that persists for billions of years, even though the fluid is always moving. The accessible picture is a moving conductor in a magnetic field, and it is an analogy with real teeth. Push a conductor through a field and charges separate, creating currents that can be measured in a lab. In a planet or star, the conductor is plasma or liquid metal, and the motion is convection plus rotation, not a hand pushing a wire. The induced currents create magnetic fields that push back on the flow through Lorentz forces, so the fluid is steered by the field it helps create. The system becomes a feedback loop where motion creates field and field reshapes motion, and stability is a dynamic balance. A dynamo is not a static magnet because it is a living circuit that can strengthen, weaken, and reverse. Earth's geodynamo runs in the liquid outer core, and it is powered by slow cooling and compositional change. Iron alloy convects because the core cools and because light elements are released as the inner core freezes, creating buoyancy that drives motion. Rotation organizes the flow into columnar structures aligned with the spin axis, and those columns help maintain a coherent global field. The generated magnetic field shields the atmosphere from much of the solar wind, reducing erosion and helping preserve water over long timescales. It also records itself in rocks, which preserve past field directions and reversals as magnetic minerals lock in alignment. Earth's habitability is tied to spin through the dynamo pathway, because spin helps keep the shield running. The historical record is written in basalt and sediment. As seafloor spreads and cools, magnetic grains align with the field, then freeze in place, creating stripes of normal and reversed polarity. Those stripes helped confirm plate tectonics, showing how magnetism can reveal motion at planetary scales. Reversals, once mysterious, now appear as a natural behaviour of a turbulent dynamo, not a sign of catastrophe by itself. Yet they remind us that the field is not guaranteed because it is generated, not permanent. The question lingers. How different would Earth be if its spin was slower and its dynamo weaker? The Sun's dynamo is more complex because the Sun is stratified and differentially rotating, and because its plasma is threaded by fields across vast scales. Shear in the tachocline helps wind up magnetic fields, turning poloidal components into toroidal bands that can become buoyant. Convection in the outer envelope twists and transports those fields, breaking them into loops that pierce the surface as sunspots. The solar cycle emerges as a quasi-periodic reversal of global polarity, roughly every 11 years in sunspot number, with a full magnetic cycle of about 22 years. The cycle is not perfectly regular, and grand minima show that the dynamo can weaken for decades. Still, the cycle is a visible heartbeat of rotation-driven magnetism, and it turns the Sun into a variable star. Visually, the cycle is a slow choreography. Sunspots appear at mid-latitudes, then drift toward the equator as the cycle progresses, tracing a butterfly pattern in latitude time diagrams. Coronal loops brighten in ultraviolet, arching like luminous ribs above active regions, while the solar wind changes character with the magnetic geometry. When the global field reverses, it is as if the Sun flips its polarity without changing its identity. The mechanism is still an active research frontier, because turbulence and rotation make prediction difficult. Yet the link to spin is unmistakable, because without rotation, the organized cycle would not exist. Magnetic activity is not just a surface spectacle, because it reaches outward and presses on planets. Flares and coronal mass ejections can erode atmospheres and alter chemistry, especially when a planet lacks a strong magnetic field of its own. High-energy radiation affects ozone, ionospheres, and escape rates, and it can drive complex photochemistry that changes climate. Young fast rotators tend to be more magnetically active, which can be hostile to close-in planets, particularly around small stars with tight habitable zones. As stars spin down, activity declines, which can open a window for atmospheric stability and long-term surface water. Habitability becomes partly a story of spin evolution, because the star's day length shapes the planet's survival. This is where the narrative becomes personal, because it touches the conditions for life. A planet can sit at the right distance and still be stripped by early activity if the star remains fast and violent. Conversely, a calmer star can allow atmospheres to persist, even if other conditions are marginal. Spin, through magnetism, becomes a kind of environmental regulator, though not a benevolent one. It raises a question that is hard to avoid. When we search for habitable worlds, are we also searching for stars that have learned to slow down? Now we pivot from magnetized winds to tides, because tides trade spin for orbit. Gravity raises bulges, and bulges create torques when they are misaligned. So the geometry of deformation matters as much as the strength of gravity. If a rotating body carries the bulge ahead of the line connecting two bodies, gravity pulls it back, trying to realign the bulge with the companion. That pull transfers angular momentum between spin and orbital motion, and the direction of transfer depends on which rotates faster. Energy is dissipated as heat through internal friction, but angular momentum is mostly redistributed, not destroyed, so the system must respond by changing rotation and orbit together. The physical origin of dissipation is crucial, because tides are not perfectly elastic. Rock flexes and heats, oceans slosh and lose energy to turbulence, and even atmospheres can respond with thermal tides that shift mass. The efficiency of this dissipation is often summarized by a quality factor, Q, which encodes how much energy is lost per tidal cycle. A low Q means strong dissipation and rapid evolution, while a high Q means a more elastic response and slower change. The difficulty is that Q depends on interior structure, temperature, and even frequency, so it is not a universal constant. Tides, like winds, are invisible torques that reveal the inside. Tidal locking is the most familiar outcome, and it is a quiet end state that looks like stillness. The Moon shows the same face to Earth because its rotation synchronized with its orbit, leaving one hemisphere perpetually turned toward us. The locking timescale depends on distance, rigidity, and internal dissipation, which is why some moons lock quickly, while others resist. Many close-in exoplanets should lock quickly, especially around low-mass stars where habitable zones are close, and orbital periods are short. Locking does not mean no rotation, because the planet still turns once per orbit, but it means the same longitude faces the star. The result is permanent day and night hemispheres, and a climate problem that must be solved by circulation. The visual is stark, a world split into a bright hemisphere and a dark one, with a thin twilight ring that never moves. Yet real tidally locked planets can still have winds, clouds, and even drifting hotspots, because atmospheres transport heat. If the atmosphere is thick enough, the night side may not freeze out, and the day side may not boil away. If the atmosphere is thin, gases can condense on the cold side, potentially collapsing the atmosphere entirely. The same tidal process that locks the spin therefore sets up a long-term test of climate stability. A planet's day can become its defining vulnerability. Tides also evolve orbits, and the Earth, Moon system, is the textbook case because it is measured with exquisite precision. In the Earth, Moon system, Earth rotates faster than the Moon orbits, so Earth's tidal bulge is carried ahead of the Earth, Moon line. That bulge pulls the Moon forward, giving it orbital angular momentum and lifting it to a higher orbit. The Moon gains orbital angular momentum and moves outward, while Earth's spin slows, and the system's total angular momentum remains essentially conserved. Laser ranging measures the recession at about centimeters per year, turning a subtle drift into a number we can watch. Day length increases over geological time, and ancient tidal rhythmites record shorter days in the past, making rocks into clocks. Those rhythmites are layered sediments that preserve tidal cycles like grooves on a record. By counting patterns tied to lunar months and solar years, geologists infer how many days fit into a year hundreds of millions of years ago. The answer is not a guess, because the sedimentary rhythms are consistent and repeatable, though they require careful interpretation. The result is a deep time confirmation that Earth's rotation has slowed and that the Moon has moved outward. Tides have been editing our planet's day since before complex life, and the edit continues now. In other systems, tides can shrink orbits, and the direction of evolution flips. If a planet orbits faster than a star's rotation, the tidal torque can transfer angular momentum from orbit to spin, so the orbit decays. The planet spirals inward, and the star can be spun up slightly, though the star's large moment of inertia limits the effect. Hot Jupiters can be slowly consumed this way, depending on stellar dissipation and the planet's distance. Tides can also circularize eccentric orbits by dissipating energy at periastron, where tidal forces peak. The final architecture can look calm, but it can be the endpoint of long tidal grinding, and the calm can hide a history of loss. Tides can heat worlds and reshape atmospheres because dissipation is literally internal heating. If eccentricity is maintained by resonances, tidal flexing can be continuous, and the heating can rival radiogenic heat. Io's volcanism is powered by tides, not sunlight, and its surface is repaved by lava because Jupiter and neighbouring moons keep its orbits slightly eccentric. In icy moons, tidal heating can maintain subsurface oceans, keeping water liquid beneath kilometres of ice. For exoplanets, tidal heating could drive volcanism, outgassing, and atmospheric renewal, or it could trigger runaway greenhouse conditions that sterilise surfaces. Spin and orbit are linked to internal heat budgets through tidal dissipation, and heat budgets shape geology. The visual is a world that glows from within, not with visible light but with thermal emission and constant resurfacing. Plumes rise, fissures open, and the crust fractures under repeated flexing, as if the planet is being kneaded. In an exoplanet context, we may not see volcanoes directly, but we might see their consequences in atmospheric composition. A persistent supply of gases can hint at continuous heating, and continuous heating often points back to tides. The turning of a world can become the squeezing of a world. Rotation also shapes atmospheres directly through dynamics, and this is where spin becomes weather. The Coriolis force deflects moving air, organising weather into jets and vortices, and it does so more strongly when the rotation rate is high. Faster rotation tends to produce more, narrower jets and stronger zonal banding, because the atmosphere breaks into multiple circulation cells. Slower rotation allows larger Hadley cells and different heat transport patterns, often moving energy more directly from equator to pole. Day length controls the rhythm of heating and cooling, affecting circulation, cloud formation, and the persistence of storms. Climate is not only about distance and greenhouse gases, because it is also about how fast the planet turns. On Earth, rotation helps create mid-latitude storm tracks and trade winds, and it supports the jet streams that steer weather systems across continents. It also contributes to ocean gyres that move heat poleward, shaping coastlines and ecosystems through currents. Without rotation, the atmosphere would still move, but it would organise differently and likely transport heat less efficiently in latitude, changing temperature gradients. On tidally locked planets, circulation may form a strong day-to-night flow, with jets that depend on rotation rate and atmospheric thickness. Habitability becomes a question of whether heat can be redistributed enough to avoid atmospheric collapse on the night side. The planet's spin becomes part of its life support system. Rotation affects planetary shape and gravity fields, which feed back on atmosphere and ocean through subtle but persistent forces. Rapid rotation causes equatorial bulging and changes effective gravity with latitude. Because centrifugal acceleration reduces weight more at the equator, that influences sea level, atmospheric scale height, and the paths of winds, since pressure surfaces follow gravity. In gas giants, rapid rotation and deep convection produce banded structures and long-lived vortices, and the bands act like highways for storms. Jupiter's Great Red Spot is partly a rotation story, because shear and Coriolis help stabilize large vortices against decay. Even when chemistry and sunlight matter, rotation sets the stage, and the stage constrains every actor. Now we add catastrophes, because evolution is not always gradual. Collisions can reset spin rates and axes in a single event, and the reset can be so complete that the previous state becomes unrecoverable. They can also strip atmospheres, melt mantles, and create moons, so a change in spin often arrives with changes in composition and structure. In angular momentum terms, an impact is a sudden vector addition, where direction matters as much as magnitude. The final spin depends on impact parameter, speed, and the pre-impact spins of both bodies, and small differences can flip outcomes. Catastrophe is therefore not random chaos, but sensitive dependence on geometry. The giant impact hypothesis for the Moon is the archetype, and it is a story built from chemistry, dynamics, and angular momentum constraints. A Mars-sized body struck the early Earth in a glancing collision, energetic enough to vaporize rock and loft debris into orbit. Debris was placed into orbit and later accreted into the Moon, while Earth reassembled as a hotter, partially molten planet. The event redistributed angular momentum between Earth's spin and the Earth, Moon orbit, setting the initial conditions for tidal evolution. It also likely melted much of Earth, accelerating differentiation and shaping the early atmosphere through outgassing and loss. Our present tides and day length are downstream of that collision, and so is the existence of a large stabilizing moon. The visual is violent and luminous, a bright arc of molten ejecta, a temporary ring of rock vapor, and then a slow gathering into a single companion. Yet the evidence is subtle, residing in isotopic similarities between Earth and Moon, and in models that must match today's angular momentum. The hypothesis has evolved as data improved, because the details of mixing and disk formation are complex. Still, the central point remains. A planet's spin can be rewritten in hours, then slowly revised for billions of years by tides. Catastrophe sets the initial condition, and patience completes the edit. Uranus is the classic case of an extreme tilt, and it looks like a planet that has been knocked sideways. Its spin axis lies nearly in the plane of its orbit, creating seasons unlike any other planet, where a pole can face the sun for decades. A giant impact is a leading explanation, though multiple impacts or long-term torques are also discussed, because the system's satellites and rings add constraints. Whatever the cause, the result is a dramatic reorientation of spin, and the reorientation is preserved in the planet's geometry. The planet's moons and rings orbit in the tilted equatorial plane, showing that the system reorganized around the new axis. A single event can rewrite the geometry of an entire planetary system, and the rewrite can endure. Impacts also affect rotation rates, and the direction of change depends on how the momentum is delivered. A glancing collision can spin a planet up toward breakup, where centrifugal force would begin to tear material loose at the equator. A head-on collision can damp rotation, converting ordered spin into heat and chaotic motion, then leaving a slower remnant. Late-stage accretion is therefore a lottery of spin outcomes, with probabilities shaped by impact statistics and orbital dynamics. This helps explain why terrestrial planet day lengths vary widely, and why obliquities can be chaotic over time. It also explains why some exoplanets may have extreme seasons or unusual climate regimes. Spin is not only inherited from disks because spin is edited by violence. Catastrophes are not limited to planets, because stars also interact and sometimes merge. Stellar encounters and mergers can spin stars up and mix their interiors, altering lifetimes and surface abundances. In dense clusters, close interactions can exchange angular momentum and create rapid rotators, leaving behind stars that look younger than their neighbours. Mass transfer in binaries can spin up an accreting star to high fractions of breakup speed, because accreted material arrives with orbital angular momentum. Some blue stragglers may be merger products with altered rotation and rejuvenated appearance, a kind of stellar disguise. Even in stellar populations, spin can be a fossil of interaction history, and the fossil can mislead if we ignore it. All of this returns to a single theme. Angular momentum is conserved globally, but it migrates between reservoirs, and the migration is the real narrative of spin evolution. It can live in spin, in orbit, in winds, in magnetic fields, and in ejected debris, and each reservoir has its own timescale. Evolution is the story of which reservoir dominates at a given time, and dominance can shift as conditions change. That dominance controls magnetic activity, climate, and stability, and it can determine whether a system is quiet or eruptive. Spin becomes a living variable, not a leftover, and living variables demand attention. Now we build tension by pushing rotation toward extremes. Faster spin strengthens Coriolis effects, increases oblateness, and can intensify dynamos, so the world becomes more structured and more constrained by its own turning. Faster spin can also store enormous rotational energy, especially in compact objects where mass is packed into small radii. At some point, rotation stops being a gentle kinematic detail and becomes a driver of exotic physics, where classical intuition begins to fail. The faster the spin, the stranger the rules feel, because speed approaches limits set by gravity and relativity. Extreme rotation is where nature shows its sharp edges. Neutron stars are where the accounting becomes brutal, because collapse compresses matter and amplifies every conserved quantity. Collapse shrinks a stellar core to a city-sized object, and conservation spins it up, often to periods of milliseconds. Magnetic fields can be amplified to enormous strengths, either by flux freezing during collapse or by dynamo action. In the newborn star's turbulent interior, the rotational kinetic energy can rival the energy released in supernova explosions, so spin is not a side effect but a major energy reservoir. Spin down through magnetic dipole radiation and particle winds becomes measurable as a steady lengthening of the period, and the rate reveals torque. A neutron star is a dynamo and a clock, but it is also a bomb with a fuse, because rotational energy can power outflows. Pulsar timing shows how clean the clock can be, and it is clean precisely because the object is so compact. Each pulse is a rotation marker, and long-term stability can rival atomic clocks, allowing tests of gravity and measurements of tiny accelerations. Yet the clock can jump through glitches, showing that the interior is not rigid and that angular momentum can be stored in hidden components. Superfluid vortices can pin and unpin, transferring angular momentum to the crust in sudden events that change the observed period. The star's spin is therefore both precise and alive, revealing internal physics we cannot reproduce on Earth. Rotation becomes a probe of matter at nuclear density, and the probe is built from timing. Magnetars push the dynamo story further, and they do it by making magnetic energy the dominant actor. Their magnetic fields are so strong that they can fracture crusts and power giant flares, releasing bursts of X-rays and gamma rays. Rotation may be slower than in millisecond pulses, but the magnetic energy is extreme, and the field can twist the magnetosphere into unstable configurations. The link to spin is still present through formation, because rapid early rotation may help generate strong fields before the star breaks. In these objects, magnetic stresses dominate surface behavior, and the environment becomes hostile to nearby space. Spin, field, and catastrophe converge, and the convergence is observable across the galaxy. Black holes raise the tension again, because spin becomes geometry rather than a material surface turning. A rotating black hole drags spacetime around it, a relativistic form of angular momentum storage called frame dragging. The spin sets the size of the ergosphere and affects the innermost stable circular orbit, changing how close matter can orbit before plunging inward. Accretion disks and jets respond to that spin, and energy can be extracted through electromagnetic processes that tap the black hole's rotation. The word spin stops meaning a surface turning, because there is no surface in the ordinary sense. It becomes a distortion of space and time, and that distortion shapes everything nearby. This is the transition we have been earning, and it ties the chapter's threads into a single rope. We began with line broadening and spots, with winds and tides and impacts, and each method showed spin changing through interaction. We end with clocks so precise they test gravity, and with rotation so intense it reshapes space-time, turning angular momentum into curvature. The angular momentum trail leads from weather to dynamos to relativistic frame dragging, and the scale changes without breaking the logic. The universe refuses to keep still, and at the highest spins it refuses to keep space still either. The same conserved quantity becomes a different kind of reality. Follow the angular momentum trail into the relativistic realm. Neutron stars and black holes will show what spin becomes when matter is crushed and time itself is forced to rotate, and when the distinction between motion and geometry begins to blur. The central question remains, but the answer will now be written in curved space-time, where rotation changes what paths are even possible. Spin is the universe's memory of imperfection, and in the next chapter, that memory will bend the rules we live by. Look up at the night sky and you're watching a universe that refuses to keep still. Worlds turn on tilted axes, stars revolve in crowded disks, galaxies swirl in slow spirals, and even space-time can be dragged by rotating mass. The real mystery is not that things move through space. It is that almost everything spins, and it keeps spinning long after the original push is forgotten. Chapter 5 pushed rotation toward extremes and promised a relativistic payoff, where the bookkeeping of angular momentum becomes inseparable from geometry. Here the payoff arrives in the densest remnants, where collapse compresses angular momentum until it becomes power, hazard, and curvature. We return to the central question with sharper edges than before. Why does the universe produce spin at every scale, and what started that rotation in the first place? A massive star ends its life with a core that can no longer support itself against gravity. Nuclear fusion has built an iron-rich center, and iron cannot release energy by further fusion, so the pressure supply fails. Gravity wins in milliseconds, the core collapses, and the radius shrinks by orders of magnitude. Angular momentum is not created in that collapse. It is concentrated, because the moment of inertia plummets, while the total angular momentum largely persists. The figure skater logic becomes brutal at nuclear density. where matter is packed like an atomic nucleus stretched to stellar size. A core rotating modestly before collapse can become a neutron star spinning tens to hundreds of times per second. The newborn object is only about 20 kilometers across, yet it can carry the rotational memory of a star millions of kilometers wide. Collapse does not need a special engine to make fast spin. It only needs a small initial asymmetry and a way to keep angular momentum from escaping. That escape is not hypothetical, because real stars shed angular momentum throughout their lives. Stellar winds carry it away, magnetic fields couple spinning gas to outflowing plasma, and expanding envelopes act like braking weights at the end of long arms. In close binaries, tides can transfer spin into orbit, or orbit into spin, depending on the configuration. By the time the core collapses, it may already be a stripped-down record of earlier torques. Even so, the collapse is so violent that whatever rotation remains becomes amplified into a new regime. In the supernova itself, the collapse triggers a rebound and a shock, and neutrinos flood outward with almost unimaginable intensity. Those neutrinos carry energy away, and in principle, they can also carry angular momentum if the emission is asymmetric. The explosion can therefore modify the spin, though the sign and size depend on complex hydrodynamics. Convection, rotation, and magnetic fields can imprint structure on the newborn remnant. The result is a compact object whose spin is both inherited and edited by catastrophe. Neutron stars are not smooth balls of matter, and their internal architecture is one of modern physics' most stubborn unknowns. They are stratified, with a solid crust over superfluid and superconducting interiors, and their structure depends on an uncertain equation of state. That uncertainty matters because it sets the star's radius and moment of inertia, which determine how much spin corresponds to a given angular momentum. It also sets how close the star can approach its rotational limits without flying apart. A difference of a few kilometers in radius can mean a large difference in allowable spin. The crust is thought to be a lattice of nuclei embedded in a sea of electrons, and deeper down the nuclei become so neutron-rich that neutrons drip out into a superfluid. Still deeper, the distinction between nuclei and free neutrons may dissolve into exotic phases. Some models allow hyperons, meson condensates, or even deconfined quark matter, though none are confirmed. The point is simple in plain language. The star's stiffness is unknown, and stiffness controls how rotation reshapes the body. A neutron star's spin is revealed as a clock, and the clock is built from magnetism and geometry. Strong magnetic fields channel particles and radiation into beams, and the beams sweep past Earth like a lighthouse. Each pulse marks one rotation, so timing becomes a direct measurement of spin. Pulsars turn angular momentum into an observable that can be tracked to many decimal places. In some cases, the stability rivals atomic clocks, and the comparison is not just poetic. Visually, the scene is stark and clean. A dark sphere, a thin cone of emission, and a rhythmic flash across a silent sky. But the mechanism is violent because the rotating magnetic field accelerates charges to near light speed. Those charges radiate in radio, X-ray, and gamma-ray bands, depending on the pulsar's age and environment. The spin is not merely a number, it is the engine that drives a magnetosphere full of currents, gaps, and pair production. Pulsar timing also shows that spin is not perfectly smooth, and the imperfections are clues to hidden layers. Glitches appear as sudden spin-ups, implying that angular momentum is stored in a reservoir and then transferred to the crust. The leading picture invokes pinned superfluid vortices that unpin in avalanches. In a rotating superfluid, angular momentum is carried by quantized vortices, tiny whirlpools whose number sets the rotation rate. If those vortices snag on the crustal lattice, they can lag behind the slowing crust, then suddenly release and dump angular momentum back. The clock stutters, and the stutter becomes a probe of matter we cannot make in laboratories. After a glitch, the spin often relaxes in stages, as if different regions recouple on different timescales. That recovery hints at superfluid dynamics, mutual friction, and the strength of pinning forces. Each glitch is a natural experiment, repeated across the galaxy, with conditions unattainable on Earth. It is also a reminder that rotation can be stored in strange ways, not just in bulk motion. Not all pulsars are born fast, and not all fast pulsars are born that way, which is where the narrative gains a second act. Many of the fastest are millisecond pulsars, spinning hundreds of times per second with remarkable stability. Their origin often requires a chapter after the supernova, written in the quiet persistence of a binary system. They are recycled in binaries, spun up by accretion, that transfers orbital angular momentum onto the neutron star. The universe turns companionship into a torque. In a low-mass X-ray binary, gas flows from a companion star and forms an accretion disk. The disk cannot fall straight in because it carries angular momentum, so it spirals inward while transporting angular momentum outward. Friction and turbulence, often described through an effective viscosity, convert orbital energy into heat and radiation. Near the neutron star, magnetic and viscous torques deliver angular momentum to the surface. Over millions to billions of years, the neutron star is torqued into a millisecond rotator. The visuals here are luminous and restless. A thin disk glowing blue-white in X-rays, a stream of gas arcing through space, and a compact star swallowing matter in a steady whisper. The disk's inner edge can be truncated by the magnetic field, forming a boundary region where plasma is forced to follow field lines. As matter lands, it can create hotspots that rotate with the star, adding another layer of periodicity. Even the act of feeding becomes a timing signal. This is the same angular momentum bookkeeping we saw in star formation, now repeated in a compact remnant under harsher rules. Disks act as conveyors, moving angular momentum outward so mass can move inward. Accretion acts as a torque, and the torque can be measured through changes in spin frequency. The difference is the lever arm and the density, which make the outcome extreme. A small amount of mass added at high, specific angular momentum can dramatically change the spin. There are limits to how fast a neutron star can spin, and those limits sit at the boundary of gravity and nuclear physics. At high rotation rates, centrifugal force at the equator approaches gravity, and the star reaches a breakup frequency. The breakup limit depends on the equation of state, because stiffer matter supports larger radii and different mass distributions. A measured maximum spin would therefore constrain nuclear physics. It would tell us how compressible matter is at several times nuclear density. Rotation also reshapes the star before it breaks, flattening it into an oblate spheroid with a bulging equator. That shape change alters the moment of inertia, and it can shift the star's internal stratification. In extreme cases, a rotation can drive differential motion between layers, especially if superfluid components couple imperfectly. The star becomes a laboratory where elasticity, superfluidity, and gravity negotiate a compromise. The compromise is visible as a maximum spin. Observationally, the fastest known spins cluster below the naive breakup line, and the gap is itself a clue. That gap suggests additional regulators beyond simple centrifugal shedding, as if the universe applies brakes before the rim tears away. One candidate is gravitational radiation, which can carry away angular momentum efficiently if the star develops a time-varying quadrupole. Another candidate is a family of fluid instabilities that become active at high spin. The limits may be set by waves, not by ripping. R-mode instabilities are a key possibility, and they are conceptually elegant because they tie rotation directly to gravitational waves. They are oscillations in rotating fluids that can be driven unstable by gravitational wave emission, turning rotation into ripples in spacetime. The paradox is that gravitational waves usually damp motion, but here they can amplify it by extracting angular momentum in a way that feeds the mode. If R-modes grow, they can spin the star down until viscosity and cooling damp them. The details depend on temperature, superfluidity, and internal composition, so the instability is also a probe of the interior. Temperature matters because viscosity changes sharply as the star cools, and a newborn neutron star cools fast by neutrino emission. There may be a window where the star is hot enough for the instability to grow yet cool enough that damping is weak. Superfluidity complicates the picture because superfluid vortices and mutual friction can provide new damping channels. Composition matters because exotic particles can change bulk viscosity, altering the instability threshold. The same spin limit could therefore encode microphysics. Even without R-modes, gravitational waves can regulate spin if the star is not perfectly symmetric. A small mountain on the crust, or magnetic stresses that distort the shape, can create continuous gravitational wave emission. The effect is tiny per cycle, yet relentless over long times. The universe would be using spacetime itself as a brake. The braking would be subtle, but it would operate day after day, century after century. The phrase mountain is almost comical at neutron star scale, because the crust is so strong that a bump centimeters high can matter. Such a bump produces a quadrupole moment, and a rotating quadrupole radiates gravitational waves at twice the spin frequency. Detecting that signal is difficult, yet the search is ongoing, because a detection would reveal both the star's asymmetry and its internal stresses. It would also complete a thematic loop, where spin creates waves that carry spin away. So neutron stars sharpen the central theme, and they do it with clocks and catastrophes. Spin is the universe's memory of imperfection, amplified by collapse and preserved by conservation. Yet at the edge of physics, that memory can leak away through channels that only exist in relativity and nuclear matter. The fastest clocks are also the most vulnerable to exotic losses. They are precision instruments built from violence. Now we step from neutron stars to black holes, where the meaning of spin changes. A neutron star has a surface and a material interior, even if exotic and partially unknown. A black hole has an event horizon, and the region inside is causally disconnected from us. Spin still exists, but it is defined by the geometry outside the horizon. The object becomes less like a thing and more like a rule for spacetime. In general relativity, an isolated black hole is described by a small set of parameters, an austerity sometimes called no hair. Mass is one, spin is another, electric charge is allowed in theory, but astrophysical black holes are expected to be nearly neutral because surrounding plasma quickly cancels charge. The simplicity is startling because it suggests that collapse erases detail while preserving a few conserved quantities. Rotation is one of the survivors. Spin is captured by a dimensionless parameter often written as A or AE, and it is built to be a pure comparison rather than a unit-bound number. It compares the black hole's angular momentum to the maximum allowed for a given mass. When A is near zero, the hole is close to non-rotating and described by the Schwarzschild solution. When A approaches 1, the hole approaches maximal Kerr rotation. The geometry becomes increasingly twisted. Maximal does not mean infinite speed, and it does not mean a solid surface whirling like a wheel. It means the horizon and spacetime geometry reach a limit where further angular momentum would remove the horizon and expose a naked singularity. Cosmic censorship is not proven, yet the expectation is that realistic processes keep astrophysical holes below the exact mathematical limit. In practice, accretion physics also appears to impose a ceiling slightly below 1. Radiation and magnetic stresses can carry angular momentum away as the hole is fed. Black hole spin is not a side detail, because it sets the rules for orbits and energy release. It sets the radius of the innermost stable circular orbit, the ISCO, which determines how close matter can orbit before plunging. A higher spin allows stable orbits closer to the horizon for prograde disks, increasing the efficiency of converting gravitational energy into radiation. Spin therefore changes how bright an accreting black hole can be for the same mass supply. It changes the balance sheet of gravity. The ISCO is more than a radius on a diagram because it marks a transition in the disk's behavior. Outside it, gas can orbit many times while slowly drifting inward, losing energy through radiation. Inside it, stable circular motion is no longer possible, and the gas plunges on a rapid trajectory toward the horizon. The location of that boundary imprints itself on the spectrum, the variability, and the disk's temperature profile. By moving the boundary, spin changes what we can observe. How do black holes get their spin, and how much of it is birthright versus later growth? Part is inherited from the collapsing star that formed them, though angular momentum can be lost during stellar evolution and explosion. Part is built later by accretion, because in falling matter carries angular momentum that can align and spin up the hole. Part is delivered in mergers, where orbital angular momentum is converted into the final black hole spin. Each pathway leaves a different statistical fingerprint. Accretion can be a spin amplifier if the disk's angular momentum is coherently aligned over long periods. Each parcel of gas adds angular momentum at the ISCO, and the hole's spin evolves toward an equilibrium set by the balance of captured angular momentum and emitted radiation. If accretion is chaotic, arriving in misaligned episodes, spins can remain moderate because vector addition cancels. The distribution of spins becomes a fossil of feeding history. It is a record written in directions, not just magnitudes. That directional story matters because alignment is not automatic, especially in turbulent galactic centers. Gas can arrive in clumps, streams, or warped disks, each with its own angular momentum vector. Over time, the black hole can be torqued to follow the dominant flow, but the process can be slow and episodic. The result may be a spin axis that wanders and a jet that changes its aim. The sky can carry those traces in bent radiolobes and misaligned structures. Mergers add a different signature, and they are among the cleanest tests of relativity's predictions. Two black holes orbit, radiate gravitational waves, and spiral together, shedding energy and angular momentum into spacetime. The final spin depends on the mass ratio and the initial spin vectors. Alignment can produce a rapidly spinning remnant. Misalignment can produce a remnant with a tilted spin and a recoil kick. In extreme cases, the kick can eject the remnant from its host environment. The merger is also a conversion engine, because much of the orbital angular momentum does not end up in the final spin. It is carried away by gravitational waves, which act as a channel for both energy and angular momentum. The waveform therefore encodes the bookkeeping, and the bookkeeping is relativistic. What is lost, what is kept, and what is redirected into a recoil all depend on the geometry of the system. Spin is not just a property after the fact, it is an actor during the plunge. We cannot see a black hole directly in most cases, so spin must be inferred from its effects on nearby matter and light. In X-ray binaries and active galactic nuclei, the inner accretion disk is the key laboratory. The disk's hottest regions emit X-rays, and those X-rays interact with iron and other elements in the disk surface. Relativity shapes the spectrum, and the shaping depends on spin. The spectrum becomes a map of motion in curved space-time. X-ray reflection spectroscopy uses the broadened iron Carr line, a feature produced when X-rays illuminate the disk and iron atoms fluoresce. The line is distorted by Doppler shifts from orbital motion and by gravitational redshift near the horizon. A higher spin moves the ISCO inward for prograde disks, so the line gains a stronger red wing from deeper gravitational potential. By modelling the reflection spectrum, astronomers infer the inner disk radius, and thus the spin. The method is powerful because the distortion is a relativistic signature, not a subtle detail. The visual counterpart is dramatic. A narrow line in the laboratory becomes a smeared asymmetric arc in the sky. The blue side is boosted by material racing toward us, while the red wing stretches as photons climb out of the gravitational well. Light bending also changes what parts of the disk we see, because photons can be curved back toward the observer. The line profile is therefore a composite of velocity, gravity, and viewing angle. Spin enters by changing where the brightest inner rings can exist. The continuum fitting method uses the thermal emission from the disk itself, and it is rooted in the idea that a thin disk has a predictable temperature gradient. In certain stellar mass black holes, the disk spectrum approximates a multicolour blackbody with a temperature profile set by the inner radius. If the black hole mass, distance, and disk inclination are known, the inferred inner radius gives the spin. The method is sensitive to assumptions about disk thickness and torque at the ISCO, so it is powerful but conditional. It works best when the disk is in a stable, thermal state. In practice, the challenge is that real disks are not perfect textbooks. They can puff up at high accretion rates, they can develop coronae that scatter photons, and they can have returning radiation that heats the inner regions. Each effect can bias the inferred radius if not modelled carefully. Yet when the conditions are favourable, the method provides a complementary view of the same boundary. Two different spectral approaches can converge on a single spin estimate, and that convergence is its own kind of evidence. Gravitational waves add a third route, and it is conceptually cleaner because it does not rely on plasma behaviour. In a merger, the inspiral waveform encodes the spins through precession and phase evolution. If spins are tilted, the orbital plane can wobble, imprinting modulations in the signal. After the merger, the remnant rings down in quasi-normal modes that depend only on mass and spin. Measuring the ring-down frequencies and damping times yields the final spin, turning space-time vibrations into a spin meter. The black hole becomes an instrument that plays its own parameters. There is also historical weight here, because the Kerr solution itself was once a mathematical object waiting for an astrophysical role. The idea that black holes could spin, and that spin would matter observationally, matured alongside X-ray astronomy and later gravitational wave detection. Each new window made the abstract more tangible. What was once a parameter in a metric became a measurable property of real objects. The story is a reminder that theory and observation co-evolve. These measurements connect back to our theme of persistence, because spin survives processes designed to erase detail. Spin survives collapse, survives accretion, survives mergers, and then announces itself through light and gravitational waves. Yet the most important point is not that spin exists. It is that in relativity, spin changes what spacetime does. Rotation is no longer just motion. It is a source of structure. A rotating black hole drags inertial frames, and the phrase is literal in the language of general relativity. This is frame dragging, also called the lens, Thirring effect in the weak field limit. The idea is that spacetime is not a passive stage. A spinning mass twists the local definition of non-rotation, so freely falling gyroscopes precess. Even straight paths are subtly redirected. The effect was once a theoretical prediction, and it took decades to become an experimental target. Around Earth, the precession is tiny, yet measurable with exquisite instrumentation, and it confirms that rotation influences spacetime. Around a black hole, the same effect becomes strong enough to shape the behavior of disks and jets. The scale changes, but the principle is the same. Spin reaches outward through geometry. Around a black hole, frame dragging becomes strong, and it reorganizes orbital motion in a way Newton could not have anticipated. Orbits that are tilted relative to the spin axis experience nodal precession, and the precession rate rises sharply toward the horizon. An accretion disk that is misaligned can warp, because inner rings precess faster than outer rings. Viscosity and pressure then couple rings, producing the Bardeen, Peterson effect, where the inner disk aligns with the black hole spin. The disk becomes a twisted sheet, settling into a new plane. This precession is not only geometry, it can become an observable clock in X-ray variability, where brightness flickers with quasi-regular rhythms. Quasi-periodic oscillations in X-ray binaries may be linked to lens, Thirring precession of the inner flow, though models compete. If the link is correct, timing becomes a probe of spin and disk structure, echoing pulsar timing in a different regime. The clock is no longer a beam from a surface, it is a wobble in a flow. Frame dragging also sets the stage for the ergosphere, one of the most counterintuitive regions in astrophysics. In the Kerr metric, there is a region outside the event horizon where no observer can remain stationary relative to distant stars. Spacetime itself is dragged around so strongly that all time-like paths are forced to co-rotate. The boundary of this region is the static limit, and between it and the horizon lies the ergosphere. It is a place where standing still is not an option. The ergosphere matters because it allows energy extraction, and it does so without violating conservation laws. In the Penrose process, a particle enters the ergosphere and splits into two fragments. One fragment falls into the black hole on a trajectory with negative energy as measured at infinity. The other escapes with more energy than the original, extracting rotational energy from the hole. The black hole loses spin, and the universe gains usable energy. The Penrose process is a conceptual proof that spin is stored energy in the geometry, and it helped clarify what rotation means in general relativity. Yet in astrophysics, the more important extraction mechanism is electromagnetic, because space near accreting black holes is filled with plasma and magnetic fields. The Blandford-Znajek mechanism describes how magnetic fields threading the horizon can tap rotational energy and launch jets. The black hole acts like a rotating conductor in a magnetic circuit, with the disk supplying the field and plasma completing the circuit. The extraction becomes continuous rather than episodic. In Blandford-Znajek, frame dragging twists magnetic field lines, inducing electric fields and currents in the surrounding plasma. The electromagnetic torque extracts angular momentum from the black hole and sends energy outward along the rotation axis. The outflow becomes a relativistic jet, collimated by magnetic stresses and shaped by the surrounding disk and wind. Spin becomes a power source that can rival the radiative output of the entire accretion disk. The jet is rotation made visible. Visually, jets are among the most cinematic structures in the universe. Narrow beams emerging from a dark center, threading through glowing gas, and terminating in bright shocks far away. Close to the black hole, the jet is invisible except through its effects, but farther out it lights up in radio and sometimes X-rays. Knots appear where the flow compresses or interacts with its environment. The jet's straightness is itself a clue, because it suggests magnetic collimation over enormous distances. A small engine produces a large, coherent structure. Jets are where the chapter's drama becomes galactic, because they connect the smallest scales to the largest. A supermassive black hole can be smaller than the solar system, yet its jets can extend for hundreds of thousands of light years. The energy is not produced by fusion or by starlight. It is produced by gravity and rotation, converted into electromagnetic outflow. The conversion is efficient enough to matter on cosmic scales. These jets can outshine galaxies in certain bands, and they reshape their environments through pressure, heat, and turbulence. In clusters of galaxies, jets inflate bubbles in hot intracluster gas, and those bubbles rise like buoyant balloons through a thin, X-ray bright atmosphere. The bubbles do work on the surrounding gas, stirring it and preventing it from cooling too quickly. This feedback helps solve the cooling flow problem and regulates star formation in the central galaxy. Spin, through jets, becomes a lever in galaxy evolution. On smaller scales, jets can also clear gas from galactic nuclei and heat the interstellar medium, changing the conditions for future star birth. They can trigger star formation in compressed regions while suppressing it elsewhere by raising turbulence and temperature. The net effect depends on coupling efficiency and environment, but the theme is consistent. Angular momentum stored in a black hole can influence the fate of billions of stars. A parameter of spacetime becomes a parameter of ecology. This returns us to a tension set up earlier about survival and regrowth, because galaxies are not static sculptures. Galaxies are battered by mergers and inflows, yet thin disks persist or reform, implying that angular momentum is repeatedly protected or rebuilt. Feedback from central black holes is part of that story, because it can prevent runaway central condensation and preserve angular momentum in extended gas. Spin is not only a property of disks, it can be a regulator that decides whether disks remain cold enough to stay thin. Spin direction also reappears as an unresolved thread, and it complicates the idea of a single stable axis. Accretion can align a black hole with its disk, but chaotic feeding can keep orientations wandering. Mergers can flip spins and produce misaligned jets, leaving radio structures that record past axes. The universe does not enforce a universal alignment. It adds vectors, and the sum becomes history. We read that history in bent jets and warped disks. At this point, the mystery becomes philosophical, because general relativity changes the category of rotation. In Newtonian intuition, rotation is motion through space, and space itself is an unchanging backdrop. In relativity, rotation can reshape the local structure of space-time, changing which paths count as straight and which observers can stand still. Spin becomes geometry, and geometry becomes destiny for nearby matter and light. The distinction between motion and structure begins to blur. This is why the climax matters for the central question, and why the question refuses to stay purely mechanical. Conservation explains why rotation persists and amplifies under collapse. It does not explain why there was any angular momentum to conserve. Yet in the relativistic regime, rotation is so consequential that it feels almost inevitable, as if any imperfection must be magnified into a dominant feature. The universe seems eager to turn small twists into large consequences, so we ask the question in its sharpest form, with the extremes of neutron stars and black holes as our evidence. If spin is everywhere and so persistent, is it simply the unavoidable outcome of gravity plus small asymmetries? Or does it hint at something deeper about initial conditions, about how the early universe broke symmetry and distributed angular momentum across scales? Is spin merely conserved, or is it seeded in a particular way? Neutron stars and black holes suggest a partial answer, and the partiality is important because it leaves room for wonder. Once angular momentum exists, the universe has many ways to store it and few ways to erase it quickly. Collapse concentrates it, accretion redistributes it, mergers remix it. Relativity then turns it into frame-dragging ergospheres and jets that broadcast spin across intergalactic space. The mechanisms differ, but the persistence is consistent. Yet the origin gap remains, and this chapter makes it harder to ignore because the endpoints are so natural. The most extreme rotators are not rare curiosities. They are endpoints that appear naturally in stellar evolution, and their spin histories are written by the same cosmic web of torques, inflows, and interactions that shaped galaxies. The small initial twist is amplified until it becomes a lighthouse, a gravitational wave signature, or a jet that heats a cluster. The amplification is routine, but the initial twist is still mysterious. Spin is the universe's memory of imperfection, and here we see the memory become an engine with multiple faces. A millisecond pulsar turns that memory into a clock, steady enough to test gravity and map binary motion. A Kerr black hole turns that memory into curved space-time that cannot stay still, forcing nearby matter to precess and align. A jet turns that memory into feedback that can regulate star formation across a galaxy. The same conserved quantity becomes timing, geometry, and power. Now we pivot outward again, because the final chapter must test whether the universe keeps any global memory. We zoom back to the larger scales to ask whether cosmic spin has a preferred direction, whether galaxies align, and what the distribution of angular momentum says about the universe's origin. The question becomes statistical and cosmic again, and the tools shift from individual objects to populations. If spacetime can be dragged locally, could the cosmos itself carry a faint primordial twist? We end where we began, under a sky that refuses to keep still, and the stillness we imagine is revealed as an illusion. The real mystery is not motion. The real mystery is the persistence of spin, from dust grains to black holes, and whether that persistence is merely physics or a clue to beginnings. The universe keeps turning, and it invites us to ask what first set it in motion. Look up at the night sky and you're watching a universe that refuses to keep still, even when the stars seem pinned in place. The real mystery is not motion through space because everything moves. It is that almost everything spins, and it keeps spinning, quietly, stubbornly across cosmic time. To resolve the central question, we do bookkeeping because nature is relentless about accounting. Angular momentum is the cosmic ledger, a conserved quantity that forces every gain to be paid for somewhere else. In plain terms, it is turningness, measured as mass times speed times distance from an axis. It can hide in spin, in orbit, in disks, in jets, and in the twisted geometry around black holes. Start close to home, where intuition fails first and familiarity becomes misleading. In the solar system, the Sun holds most of the mass, yet it holds little of the angular momentum. Most of the budget sits in planetary orbits, dominated by Jupiter's wide, fast-moving path. If you could see the ledger as a glowing diagram, the Sun would be a massive bright dot with a surprisingly small rotational arrow. That contrast is the first lesson of the ledger, and it is a geometric one. Angular momentum prefers large lever arms, so distant orbits can outweigh rapid spins. A small body far out can carry more angular momentum than a massive body turning quickly. The equation is simple, but its consequence is strange. Distance can beat heft. This is why the solar system's history matters, not just its present. Early on, the Sun likely spun faster, but magnetic fields coupled it to the disk and later to the solar wind. Charged particles flowing outward acted like a braking system, exporting angular momentum into interplanetary space. The planets, meanwhile, kept their orbital share, because orbits are efficient vaults for angular momentum. The same accounting repeats in smaller systems, where the universe builds structure from collapsing gas. In star formation, collapsing gas cannot simply erase its initial twist, so it builds disks and binaries. Even a cloud with only a faint initial shear will spin up as it contracts, because the moment of inertia drops. The disk stores angular momentum while mass moves inward, and fragmentation converts spin into orbital motion. Visually, it is a familiar spiral, but on a scale that dwarfs imagination. A cold, dark molecular cloud begins to glow in infrared, then flattens into a rotating pancake of dust and gas. Shocks ripple through it, turbulence stirs it, and yet the net rotation persists, like a slow whirlpool that refuses to unwind. In that disk, tiny grains collide, stick, and grow, while the ledger quietly dictates what can fall inward and what must remain out. In mature planetary systems, tides and winds trade angular momentum between reservoirs, but they rarely destroy it. Energy can be radiated as heat and light, yet angular momentum mostly migrates. Earth's day lengthens because the Moon steals rotational angular momentum and moves outward, millimeter by millimeter each year. The universe can cool efficiently, but it struggles to stop a turn. Now scale up to galaxies, where the ledger becomes statistical. Simulations show dark matter halos acquire spin through tidal torques from their environment, especially before a near turnaround. In that early phase, proto-halos are not spheres, and their mass is not pulled evenly. When the inertia tensor and the tidal field are misaligned, gravity applies a net torque, and the ledger begins to fill. The spin parameter distribution stays broad and roughly log-normal, reflecting chance and neighbourhood. Some halos end up with generous angular momentum, others with little, and the difference can decide whether gas forms a thin disk or a compact spheroid. In simulation visuals, you can watch filaments feed knots of matter, while little vector arrows flicker and reorient as structures grow. The web is not a static scaffold, it is a flowing network of streams and collisions. Surveys then ask a harder question, because statistics become geometry in the real sky. Do galaxies point their spin axes randomly, or do they remember the cosmic web that fed them? The answer appears to be both, depending on mass, type, and how the sample is selected. What looks like randomness can hide weak coherence, and what looks like coherence can be amplified by selection. Low-mass disk galaxies often show alignments with filaments, consistent with smooth accretion along preferred directions. Gas arriving along a filament tends to share a common inflow direction, and that can seed a stable disk plane. More massive systems can flip, with spins tending to lie perpendicular to filaments after repeated mergers. The trend is plausible, but the uncertainties remain large. Selection effects haunt every claim of alignment, because the sky is a projection, and galaxies are messy. Inclinations are hard to measure, dust hides disks, and projected shapes confuse true 3D spins. Even defining a spin axis for an irregular or disturbed galaxy can inject bias into the ledger. A face-on disk can look deceptively round, and a warped disk can carry multiple angular momentum directions at once. Still, the emerging picture is coherent, and it matches the logic of anisotropic growth. The cosmic web supplies torques and anisotropic inflow, so spin directions are not born in isolation. Yet the web is tangled, so local coherence does not imply a universal axis. The universe can imprint patterns without choosing a single direction for everything. Now we pivot to mergers, because they are the ledger's violent audits. In hierarchical growth, orbital angular momentum is huge, and a merger can convert it into internal rotation. The same process can also randomize directions, depending on geometry and timing. Two galaxies rarely meet head-on in perfect symmetry. Most encounters are glancing, and glancing encounters are rich in angular momentum. Spiral galaxies advertise a relatively gentle angular momentum history, written into their thin, cold disks. They retain cold, rotating disks because gas can cool, settle, and rebuild after disturbances. Their thinness implies that major mergers were avoided, or that disks regrew from fresh, high angular momentum inflow. When we see spiral arms sweeping like painted commas, we are seeing order preserved against a background of chaos. Elliptical galaxies tell a different story, and their light is a clue to their kinematics. Repeated mergers heat stellar orbits, turning ordered rotation into dispersion and creating pressure-supported shapes. Stars in ellipticals move on many intersecting paths, like a swarm rather than a wheel. Some ellipticals still rotate, but their rotation often reflects the last major merger's vector sum. Mergers also leave fossils that the ledger cannot hide, even when the surface brightness looks smooth. Counter-rotating disks, kinematically decoupled cores, and warped gas layers record past accretion episodes with different angular momentum directions. The vector nature of angular momentum makes history legible, even when light is smooth. With modern integral field spectroscopy, those fossils appear as colour-coded velocity maps, quiet evidence of ancient collisions. Black holes complete the ledger's extreme column, where gravity becomes geometry. Their spin can be inherited from collapse, built by coherent accretion, or rewritten by mergers. Once present, it shapes the innermost disk, powers jets, and drags space-time into partial co-rotation. Frame dragging is not metaphor here. It is a measurable twisting of the local inertial frames near the horizon. Yet even here, the accounting is strict, and the escape routes are physical. Jets and winds can carry angular momentum away from the disk, allowing matter to fall inward. Magnetic fields threading the disk can act like a torque wrench, transferring angular momentum outward along field lines. Gravitational waves carry angular momentum away from merging black holes, leaving a remnant whose spin encodes what escaped. With the ledger assembled across scales, the temptation is to ask for a master entry. If everything spins, does the universe itself rotate, providing a single cosmic motor? A globally rotating cosmos would imprint a preferred axis and anisotropic expansion. It would be the ultimate symmetry breaking, one direction written into spacetime itself. Such a rotation would leave fingerprints in the cosmic microwave background, our oldest all-sky photograph. It would generate large-scale temperature and polarization patterns beyond ordinary density fluctuations, It could also induce vorticity that would not average away on the largest angles. In visuals, the CMB would show subtle swirls or directional gradients that refuse to vanish with better data. Observations strongly constrain this possibility, and the constraints have sharpened over decades. The CMB is isotropic to parts in 100,000, and its residual anisotropies match a non-rotating expanding universe with tiny primordial perturbations. Any global vorticity must be extremely small compared to the Hubble rate. If the universe rotates at all, it does so too slowly to serve as the engine of everyday cosmic spin. Claims of a preferred axis still appear, often framed as anomalies or alignments in low multipoles. Some analyses report subtle parity asymmetries or dipole-related patterns, and some galaxy surveys hint at large-scale spin correlations. The evidence remains contested and sensitive to systematics. The hard question is always the same. Are we seeing physics, or the fingerprints of instruments, foregrounds, and incomplete samples? So the ledger points away from a single cosmic flywheel, even if the idea remains haunting. The universe does not need a global rotation to generate ubiquitous local spins. It needs three ingredients that are unavoidable in a real cosmos. First, tiny initial asymmetries, because perfect uniformity is a mathematical dream. Inflation stretches quantum fluctuations into classical density variations, and perfect symmetry is never achieved. Those variations are small, but they are everywhere, and they set the stage. If you could rewind the universe, you would not find a featureless fog but a nearly smooth field with faint ripples. Second, gravity amplifies those variations, and tidal fields apply torques whenever shapes and pulls are misaligned. A protogalaxy is not a neat sphere, and the surrounding mass is not evenly distributed. The resulting torque is weak at any instant, but it acts for a long time. Over cosmic ages, small twists accumulate into substantial spin. Third, collapse plus conservation. The step that turns a whisper into a roar. As matter contracts, the moment of inertia drops, and any non-zero angular momentum forces higher rotation rates. Gas that can cool becomes thin and rotationally supported, so disks and rings become generic outcomes. This is the same logic as a figure skater pulling in their arms, scaled up to nebulae and galaxies. This is why everything spins without a motor, and why the effect is so widespread. Angular momentum is not created from nothing in ordinary structure formation. It is generated locally by torques and asymmetries, then preserved and concentrated as structures form. The universe does not need a crankshaft because it already has imperfections and time. Now we return to time because the ledger evolves and the entries migrate. Dissipation drains energy efficiently through radiation, shocks, and turbulence, letting matter settle into deeper gravitational wells. Angular momentum is harder to eliminate, so dissipation mostly rearranges it rather than erasing it. In practice, matter falls inward by giving its angular momentum to something else, often to outer disk material, to a companion, or to an outflow. That asymmetry between energy loss and angular momentum loss shapes the arrow of structure. Systems cool into ordered rotation while exporting angular momentum outward through disks, tides, magnetic torques, and ejected mass. The universe ages by moving angular momentum around, not by balancing it to zero. When you see a thin disk against a black sky, you are seeing a compromise between cooling and conservation. Across chapters, one principle ties the scales together, and it is as old as classical mechanics. From quantum fluctuations to cosmic web torques, from star-forming disks to relativistic frame dragging, angular momentum is the memory that survives. It is the conserved record of every slight misalignment that gravity had time to amplify. The ledger is not just a metaphor. It is a constraint that shapes what the universe is allowed to become. So what started the rotation in the first place, and why does it persist so stubbornly? Not a cosmic crank, but the inevitability of imperfection in an expanding, clumping universe. Once any region has a tiny offset, gravity turns that offset into torque, and conservation makes the result persistent. The deeper question is unsettling. If perfect symmetry is impossible, was spin always guaranteed? The haunting part is that the ledger never fully closes locally, even when a system looks settled. Angular momentum can be shuffled into orbits, hidden in halos, stored in spins, or carried away by radiation and outflows. But it rarely disappears, so the past keeps steering the future. Every rotation you observe is partly a record of what could not be cancelled. We end with what we still do not know, because the ledger is complete only in principle. We do not yet track in detail how baryons and dark matter share angular momentum during galaxy formation. Feedback from stars and black holes can eject low angular momentum gas and reshape disks, but the net accounting is still uncertain. Even the timing matters, because early outflows can change what later inflow is able to build. We also do not fully understand why some disks survive repeated perturbations while others become spheroids. We are still mapping how filamentary inflow, mergers, and internal instabilities trade angular momentum over billions of years. Even the statistics of spin alignments remain limited by measurement and bias. Each new survey tightens the ledger, yet it also reveals how many entries were smudged by projection. Yet the central question now has an answer that fits every scale we have visited. The universe spins because it cannot help but remember every tiny imbalance, and because nothing, once set turning, finds an easy way to stop. The sky is not restless by choice. It is restless by conservation. Across every chapter, the pattern kept repeating, from a wobbling dust grain to a spinning black hole. Stillness was never the default. Angular momentum, L equals I omega, doesn't explain the first push, but it explains the stubborn persistence and the dramatic spin-ups as matter shrinks. We saw how gravity amplifies tiny asymmetries, how tidal torques in the cosmic web seed rotation in dark halos, and how cooling baryons turn that inherited turningness into disks. We watched spin become both obstacle and engine, forcing accretion disks, powering MRI turbulence, and launching jets and outflows that carry excess angular momentum away. We followed the cosmic ledger as it migrates between spin and orbit, gets rewritten by tides and impacts, and is audited violently by mergers that leave kinematic fossils. And at the edge of physics, we saw rotation etched into space-time itself, where frame dragging makes standing still impossible, and spin becomes a reservoir that can feed jets and gravitational waves. What remained unresolved was never whether the universe can keep turning, but why turning appears so generically, without a global cosmic whirl. The early universe was almost uniform. The CMB tells us any overall rotation is tiny, and linear flows tend to lose vorticity as space expands. Yet imperfections survive, and once collapse becomes non-linear, shell crossing, shocks, turbulence, and baroclinic twists, curl is reborn, then preserved, concentrated, and redistributed. Tidal torque theory gives a repeatable engine, misalignment between shape and surrounding tides, building a broad distribution of spins that later accretion and mergers modify. The details are still being argued in the margins, how baryons trade angular momentum with dark matter, which feedback histories let thin disks survive or regrow, and when flips, warps, and counter-rotation become long-lived. Even the tantalizing hints of large-scale alignments sit on a knife edge, poised between new cosmology and the quiet tyranny of systematics. But the deeper revelation is simpler and stranger than any single mechanism. Spin is the universe's memory of imperfection, a conserved record of tiny asymmetries that gravity can't help but amplify once matter begins to clump and cool. So, what lit the first match? Who or what gave the universe its initial shove, and why does it never stop turning? The honest answer is that no single hand had to strike it, because the universe didn't need a special twist. It only needed not to be perfectly symmetric. Quantum fluctuations stretched by inflation, minute density ripples in the CMB, and the lumpy geometry of the cosmic web provide countless small lever arms, and gravity does the rest. Rotation is not a cosmic preference for a particular direction. It is the generic outcome of collapse in an imperfect world, with angular momentum acting as the bookkeeper that refuses to let the imbalance be forgotten. And that reframes the mystery from where did spin come from, to why is perfection so rare that spin becomes inevitable? In a cosmos where the breaks are weak, where torques are everywhere, and where every merger adds vectors rather than erasing them, the question isn't why things rotate, it's how anything ever manages to stop. If there is a final image to carry with you, let it be this. Every whirl is a fossil, a signature of ancient forces written in motion. A planet's day, a star's dynamo, a pulsar's ticks, a galaxy's disk, and a black hole's dragged space-time are all telling the same story. That the universe remembers its smallest unevenness and builds vast structures from it. So the next time you look up at the night sky, listen for the quiet accounting behind the light and ask what each spin axis is pointing back to. And if you want to help settle the last open questions, Follow the new maps being drawn by CMB polarization, deep galaxy surveys, and gravitational wave catalogues, because the cosmos may yet reveal whether its rotations are merely local echoes or the faintest hint of a deeper shared beginning. So what lit the first match? Who or what gave the universe its initial shove, and why does it never stop turning? The honest answer is that no single hand had to strike it, because the universe didn't need a special twist. It only needed not to be perfectly symmetric. If there is a final image to carry with you, let it be this. Every whirl is a fossil, a signature of ancient forces written in motion. Spin is the universe's memory of imperfection, and in that memory the cosmos keeps becoming. And if you want to help settle the last open questions, follow the new maps being drawn by CMB polarization, deep galaxy surveys, and gravitational wave catalogues, because the cosmos may yet reveal what started the turning.